All right, I'm just gonna kick us off here. It is 9:01. I know people are still trickling in, but, well, I was gonna say we don't have time to waste, but I do have a 15-minute welcome slot, so I suppose we have a little bit of time to waste. All right, so I'm Rowan. If you guys haven't met me, I did have a session yesterday, but just to introduce myself, I'm a rising junior at Colgate University, majoring in computer science and geography. And I'm going to be the MC for today, which means I'm going to take the role I tend to take in group projects, which is to be the Debbie Downer. If you are going over on time, I will cut you off. It is not personal. We have a lot of stuff to do today, and I just want to make sure we get to everybody in the schedule. So, just as a reminder, for anyone who signed up for trainings 3 and 4, those do start at 9:30 upstairs. So those will be starting very shortly. Additionally, at 3:45, there will be a tour of the Mesa Lab. This is limited to 30 people, and there is a sign-up sheet at the front of the registration desk. The shuttle is going to leave at 3:30. You also may carpool if you have a car. Additionally, give me 1 second to pull up the information here. Allison's husband will be playing bluegrass music at Asher Brewery starting at 5 p.m. Well, actually starting at 6 p.m. I just got an update. And there will be a taco food truck at the brewery for those of you who would enjoy that as well. Also, there is a raffle today. There are 2 raffles today, in fact, because we did not do one yesterday because there were not a ton of people here at the end of the day. The first raffle will be right before lunch, and the second raffle will be at the end of the day. So please stick around for 2 chances to get a lovely UIFCW mug. And yeah, so in that, we have a good 13 minutes. I will give some time back, but I am going to, and let me just actually flip through these, make sure there's nothing. There's me. Funny to have a picture of me, considering I'm here. Yep. Which event? It is not. That's just, Allison asked me to announce that. Oh, it is, no, it is at Asher. It's a different. Oh, no. No. Flip through our schedule. Here. Oh, yes. One more announcement. Please do take the UIFCW post-event survey. I know some people are leaving early, so you can take that today, take that tomorrow. It'll be up again at the end of the day, but I'll give you guys a few seconds to scan the QR code there if you would like. All right. And with that, if we could switch the screen share. Great. Okay. Are we? Great, I'm gonna hop into a short weather briefing for this morning. So it is currently 66 degrees with a dew point of 59, which is a little bit humid for here. And with that, we have a chance of scattered showers and thunderstorms starting about noon, going through the day. And if we look at the water vapor, we can see why. There's a pretty large long wave trough bringing some southwesterly flow over the Rockies. And just to do a quick look at the cams, this is obviously just one cam run. You can see the HRRR is outputting some scattered thunderstorms throughout the day. Now, if we're looking through for the days 2 and 3, we can see the overall pattern stays in place. And so on the forecast, similar chances for showers and thunderstorms. Also today, we are in a marginal risk from the Storm Prediction Center for perhaps some gusty winds, small hail. And if we jump over to the National Hurricane Center, we can see there is, finally, some development in the tropical Atlantic. It is still just a 30% chance, so I mean, get ready for all of the people posting our 360 GFS runs, but not much going on there. But in the Eastern Pacific, we do have a tropical cyclone coming off of the coast of Mexico here that is likely to develop very soon. So that is the weather briefing, and I will be happy to give the time back to our first panel, which is, and we'll get the screen share set back up. Perfect. Which is R2O facets and how to engage in R2O to advance the UFS. And I'd like to introduce Andrea Ray, our session chair, who will then introduce all of our panelists. So thank you all.
Hi, everybody. Good morning. This is the session on research to operations and how to engage in R2O. And we're going to be hearing from several different aspects of R2O that are related to UFS. Can we pull up most of our panelists are actually online. Can we pull up Jordan, first we'll be hearing from Kevin Garrett, and there's a little bit more information on there. He's the Modeling Program Director at Weather Service Science and Technology Integration. Jordan Dale, who's the Test Beds Program Manager at the Weather Program Office. I'm going to talk a bit about the Test Beds and Proving Grounds Coordinating Group as a whole, and then we're going to have Chandra Chandragunta and Jacob Carley and Jim Nelson, who are going to be on the panel in a bit. And I guess they're not on screen yet, and we don't have Kevin yet. Oh. I'm looking for you on screen, and you're not on screen, so. Should we get going? All right, Kevin, I'll turn it over to you.
I am not a hologram yet. All right, thanks, Andrea. Good morning, everybody. Good to see everybody again up here. Yeah, so I'm just going to give some overview of the Weather Service perspective on research to operations, and hopefully tie that in with the larger UFS community efforts, and maybe provide some talking points or considerations to spark some panel discussion. Because this is obviously an important topic, and there's a lot of innovations we know historically with trying to transition new capabilities and operations. We throw the terms like Valley of Death around and things where there's really some interfaces that are really difficult to manage to get new capabilities into operations quickly, and so unfortunately some innovations are left out. So we'll try and address those. Let me see if I can find the pointer today. All right, so just a brief overview of Office of Science and Technology. Again, our mission is really to provide innovative, new innovations through applications of science and technology. So this is really three pillars in STI. One is, of course, environmental modeling. That's where I sit. We also have a division that's focused on tools and applications to be used by our operational forecasters, some of which provide tools or visualization or ways to analyze forecast data so that our forecasters have really accurate, reliable information they can then communicate to stakeholders or create their products and services. And a lot of this also ties in now to our social, behavioral, and economic sciences program, which has really become really important for that last critical mile and being able to provide information that is actionable. So within STI, again, I'm the program director for the modeling division. So our mission is to advance weather service integrated operational environmental modeling through open science to support accurate, reliable, and actionable analysis and forecast information. I think I mentioned this on the first day on that panel that we manage this through a number of programs of record. But we're also overseeing a variety of projects that are really focused on transitioning new modeling capabilities into operations. So I'll talk a little bit about those on the next slides. So the UFS R2O project has been around for a number of years, and really the primary focus has been to transition our operational modeling suite to the Unified Forecast System framework. So we're looking to reduce the number of components for Earth system modeling as well as the infrastructure and simplifying that. So it's easier to manage and maintain, but also hoping that through that simplification, being able to focus on a smaller set of components to really do more innovation and accelerate transition to operations. But again, the project is really focused on sort of initial transitions of our more flagship regional and global models to the Unified Forecast System. We've had a number of partners, both across NOAA as well as through the academic community and private sector over the last 6 years. And so we're finally, I think, converging to sort of that initial completion of a transition to the Unified Forecast System for all of our major modeling systems. We are focused on high readiness level, again, weather service, where we fit in, particularly with the Environmental Modeling Center, or EMC. This is their major task, is to be able to do that transition to operations and make sure that all the new code that's being delivered to these systems is meeting operational requirements. I will also say that this project itself is managed not just by OSTI, but also our partners in the Weather Program Office, including EPIC and JTTI. A little bit more about the structure. I left out that piece on the last slide. This is just another sort of way to visualize how we're supporting the building, the construction of different applications. So we have a medium range weather and subseasonal to seasonal team. We've actually sort of taken the S off of that, as we'll see on the next slide, to focus on the seasonal forecast system. We have short range weather cam focused on the RRFS version 1 and future work with MPAS, and our hurricane integrated application team focused on the hurricane analysis and forecast system. And we have a number of cross-cutting teams that are focused on various components that have intersections with each of those major applications. I mentioned the seasonal forecast system. Again, this is a separate project, mainly because there are a number of science and predictability challenges that are quite a bit different from just looking at even subseasonal timeframes. And so we wanted to make sure that we were providing really the focus of all the work that needed to be done through a separate project. And you can see the number of tasks there don't necessarily align with our cross-cutting teams on the previous slide. There are quite a few unique different focus points there. You know, not just with the different physics and focusing on ocean modeling, but also looking at coupling strategies. This is going to be an ensemble system. There's another one on infrastructure and cloud strategy, as this system is really well suited for running in a cloud environment because it takes a lot of resources to run, but it's not going to run on a high frequency cadence. It may run only one time a month. So we don't necessarily think that a strategy of buying a really large supercomputer to be able to fit this in once a month is maybe effective or efficient. So running this on the cloud is really our objective in the long term. So again, this is just looking at those major flagships that we're working through these projects to transition to operations. Excluding the HAFs, which again is really important, but we've done the major transition to the UFS there, and we're, I think, now in our third operational upgrade for the HAFs. So again, looking at focusing on the GFS and the GEFS next versions, the fully coupled Earth system model. The RFS, of course, we're working now after the field evaluation and actually handing that off to our NCEP central operations for operational implementation. And the seasonal forecast system, getting ready to run some beta prototypes in real time to do further evaluation toward operational implementation and replacement of our climate forecast system. All right, so I really wanted to focus the last few minutes on this slide and sort of talking about the R2O process. And I took this old image of the sort of R2O funnel, but all of the ways that the community and NOAA and partners interact with that funnel, and just to kind of highlight some of the challenges that remain with the R2O process. So again, looking at sort of the upper end of the funnel and where we're, hoping that there's a lot of community innovation. So I've highlighted the major efforts there in terms of developing the UFS systems, bringing in, either new components or modifying components, or, however enhancements are going to happen. Integrating with prototypes and doing a lot of testing and evaluation, perhaps getting in front of test beds, and then sort of iterating through that process as we get feedback from the users back into the development life cycle until it's really meeting the requirements for operations, both in terms of technical capabilities as well as for performance and skill forecasts. Down below, we see sort of the NCEP transition process, which seems to have maybe a little bit more complicated and a lot of other factors that need to be focused on. A major one being integration into the operational supercomputer system, which is a different platform than perhaps the developers are using and building their systems on. doing beta evaluation, retrospectives, field evaluations, which consist of running it in real time, and then ultimately, going through the NSEP process for making a decision of whether or not to implement operationally. And there's a lot of feedback given by the field that either consent to or agree to that it should go to operations or not. And if there are issues, can we address those before it goes operational? And then there's the code handoff, testing, and implementation finally. So it's a pretty arduous process. And I would say that there are a number of challenges, not just the time that it takes to go through this process, but if there are any hang-ups and you have to sort of reset, again, that's going to add to the time frame in which you actually implement. So I just highlighted a number of challenges that kind of still remain that may be worthwhile for the panel discussion in terms of the gap between these two parts of the R2O funnel. I'll say that, basically, number one, it's going to require resources from NOAA and particularly the Weather Service to integrate new modeling capabilities into the next operational prototypes. There are multiple parallel efforts going on, even within the same modeling systems, that have to be managed. This is really resource intensive. Sometimes these efforts conflict, and new capabilities may impact other new capabilities, and those need to be reconciled. There are also parallel changes to infrastructure and workflow, particularly on WCOS, where the infrastructure, the compilers, the systems changing, and that may break things, and that needs to be addressed as well. So all of these ways of sort of maintaining the system, doing the testing and evaluation, the resources needed and the time needed to do this really is exhaustive. I mentioned testing and evaluation. I think this is where sort of the hierarchical systems development can help sort of accelerate in terms of prototyping methods and sort of moving to the next phase of development and integration. I don't know how much a CI/CD paradigm is going to help accelerate a lot of the parts of this process, but I'm certainly interested to hear from folks like Jacob on how we might be able to leverage that approach. And then finally, I'll just say addressing limitations of the UFS-RDO project. So we've basically had 2 3-year projects, and they've been very successful in transitioning our operational production suite to the UFS. But the scope has been fairly static, aside from some changes due to understanding of science limitations or technical limitations and having to pivot to other solutions. But more or less, the folks that have been involved in the project have been fairly static, and we haven't had the agility to kind of pursue more broader engagement with the community. And so I'll just say, without really any formalization of the next phase of UFS-RDO, is that we're going to be really looking for more external community engagement and more targeted projects to work closely with not just the labs in NOAA, but also, of course, EMC on perhaps integrated teams to push really impactful solutions into our next operational system. So more to come there. I think with that, I'll hand it back to you. I think Jordan is next. And I'm sorry, I probably used all the extra time that Rowan gave us. So.
Thanks, Kevin. Can you hear me?
Yes, we can.
All right, thank you. Good morning. I'm Jordan Dale, and I'm the Test Beds Program Manager in the NOAA Office of Oceanic and Atmospheric Research's Weather Program Office. Before I jump into more about WPO's role in the R2O process, I'll first touch upon what WPO does. So at a high level, in WPO, we fund research to improve weather forecasts and warnings. And in order to accomplish this, we have 3 science divisions within WPO. Those are outlined on the right. It's the Observations Research Support, Earth System Research and Modeling, Science Technology, and Society. My program, Test Beds, as well as JTTI, which Chandra Kandragunta represents, we both fall under the Science, Technology, and Society, along with Social Science and Vortex. And what we do in the office is we work closely both within our divisions and also across divisions, to ensure that world-class weather research is advanced continually to improve our understanding of weather phenomena. All right, next slide. Thank you. WPO plays what I consider a central role in, along with other offices, of course, in facilitating the partnerships across the weather enterprise. And what I mean by weather enterprise is internal partners, ones that typically stand out are NOAA Research, OAR, and the National Weather Service, but also external partners, and that can be from academia, industry, also other agencies in the federal government. Now, I like to think of WPO's role as serving as the two in research to operations. So the animation on the right shows a rough example of how this looks. You can see there's lots of different things trying to come in. And in WPO, we try to funnel people to the right places to help facilitate the R2O process. Next slide. It's also important that I emphasize that research transitions are bigger than just R2O. The broader R2X space can include other things like research to applications, research to commercialization. Also, another big one in the office for us is knowledge transfers. So not always do we expect research to get to the RL8 level where it's ready for consideration for going into operations. And there's other uses too that we have on the slide here that can all help to advance the science. WPO's role in this process of R2X is to try to bring the potential end users into the full R2X process and ensure that research outputs are useful, usable, and eventually put into practice. Next slide. So for those of you in the room and on the call here, how can you best participate in making your research more useful? The big thing I want to emphasize here is coordination. And that coordination needs to take place between researchers and end users, and that needs to happen early in the R&D process. By early, what I mean is as soon as you have a proposal ready to develop, ideally that's when you want to start talking to the end users to ensure that the proposed research outputs are relevant and practical. And then it doesn't end after that. The coordination needs to continue throughout the full research project lifecycle. By talking to each other regularly, this helps ensure that research outputs are useful, usable, and eventually put into practice. Next slide. All right, so this is a diagram of kind of the example of how that coordination process ideally should look. So as I just mentioned, engagement with end users should happen before and during proposal development. This helps ensure as researchers draft their proposals that there's a practical path to transition in mind. And that doesn't always mean that, at the end of a project that the transition must happen, but at least you're working towards something that eventually down the road could transition. Now, if we fund a project, and once that project begins, the collaboration and coordination process should happen throughout the project lifecycle. And that's between the research team and whoever the end users might be. And this is really important to foster what I like to call the R2X to R process, which is an iterative back and forth that includes evaluating research outputs, getting feedback from the end users, and using that feedback to continually improve the research output. So it's not always the case that what you envision at the beginning is a static thing at the end. Oftentimes we find that iterative feedback process and coordination with end users helps refine and improve the eventual output. Now, as part of this iterative process, documenting outputs, timelines, and transition costs in a transition or knowledge transfer plan is also key for bringing everyone together to ensure that any potential roadblocks or issues are addressed at an early stage and remedied. It's also important, once you've developed a transition plan, that you continue reviewing it, keeping it updated, and really keeping it fresh with the realities of what's happening in the operational environment. And then finally, at the end of the project lifecycle, assuming all these steps have gone well, The feasibility of the research outputs can be determined with a decision for operational implementation, or oftentimes you'll find that there's the need for additional research and development work. Finally, at the top right here, there's a little box that mentions that this is an iterative process, and I think that's really important. It's okay to make changes along the way as more knowledge is discovered. And another thing I want to mention, WPO, we typically fund projects up to the RL8 level. So really that gets something right at the end stage where it's ready for that final determination if something actually can be implemented into operations, which then feeds into that last slide Kevin just showed, which also has other, complex steps to get something actually into operations. So again, it's iterative. Things can go from 4 to 7, back down to 6, start again, hopefully get up to 8. And that's really important to keep in mind, that this is a fluid process. And there's not always a quick, jump from 4 to 8 in a few years. It can take some time. All right, so that was my last slide. I will turn it over to Andrea Ray, and she'll present more about the testbed's role in R2O.
Oh, great, thank you. All right, hi everybody. I just want to acknowledge that Jim Nelson is the new chair of the Testbed and Coordinating Committee, Cross NOAA Testbed and Coordinating Committee. I'm the past chair, but Jim couldn't be here in the room, so we decided I'd give the talk. There's 13 of them. I'm not going to go through what they all are, and I'm not going to go through in a lot of detail. Oh, wait.
Could you get a little closer to the mic?
Yes, does that help?
Yes.
So, okay, so I just was acknowledging that Jim and I worked on this presentation together, and he's the new chair of the Cross NOAA Testbed and Proving Ground Coordinating Committee. And if you're interested in more details on these, Jim and I have both given talks at the most recent AMSs and at this meeting last year that were longer talks in more detail, so you can find out some more there. So I want to say what these are. They sit at this node in NOAA research and operations feeding back into research. And because this term test beds is used in some other context, in fact, it was discussed a lot yesterday in the seasonal forecast system. So I want to say how we do this and what we mean by test beds. These are multi-project, multi-year efforts that are ongoing partnerships between research and operations, and they're aimed at improving or creating new operations or operational products. So it's not like it's a data set or a set of cases, although they work on data sets and sets of cases. And so they're a major facilitator of R2O, and as Jordan was just saying, there's a lot of iteration and collaboration along the way. And one of the things they do, one of the words we end up hearing is people saying they bring tech stuff into the world. Maybe there's something new coming out of UFS. And so for an example that is the excessive rainfall outlook that's now coming out, that's been coming out of the Weather Prediction Center. So there's improvements in the prediction of extreme rainfall, but then how do you turn that into a product that's useful for people? And I just want to note that there's the online portal, testbeds.noaa.gov, that has connections. And then finally, I have this little cartoon here of a bunch of people in a car, and that's because I like people to think about the test beds as kind of a road trip. Everybody gets in the car together, operations, sometimes emergency managers, developers, people from the national centers, WFO staff, the PIs, and you get somewhere, but you learn things about each other along the way. You may take a detour, you may discover something new that you weren't expecting, and so sometimes the test beds are considered to be linear. Stuff goes in, it gets tested, it comes out, and that does happen, but a lot of other things happen too. So these are a few ways in which the test beds are integral to UFS development. And I could give you examples of a bunch of different projects for each of these, but these are just kind of the general kinds of things and a few ones. And these are abbreviations for some of the test beds. So data assimilations, Joint Center for Satellite Data Assimilation and the Developmental Test Bed Center, very involved in that. Also COMT, the only test bed that's not primarily connected to the Weather Service is the Coastal and Ocean Modeling Test Bed. Physics testing, many of the test beds are involved in this, and in particular the climate test bed has been funded by Jordan's office to do some of this. Verification, including how an innovation affects an IDSS relevant variable. So not just how it affects some other kind of verification metric, but others, and multiple test beds in various ways involved in that, including RRFS testing. There was that RRFS white paper a couple of years ago that Jacob Carley, who's online, led, and that was the result of testing and evaluation going back to at least 2017. HMT hydromat test bed recommended some modifications to alleviate some issues in RFS precipitation rates based on a number of years of testing. Another thing is developing diagnostics packages tailored to UFS. Developmental Test Bed Center has done that in particular. MET+ is one of those. Develop and demonstrate and evaluate probabilistic products and prob IDSS based on UFS output. And most of the test beds are involved in one way or another on that. And then I just, picking up on that road trip idea, this is not just linear, and probably rarely linear. Often evaluation happens over multiple years. Collaboration between test bed, comparison among multiple innovations is a common thing going on. And iteration between the researchers and the developers, including this idea of operations feeding back into research. And then engaging community, and I'll talk a little bit more about that in a second. How do we do this? These are both pictures of people in person, but now a lot of this is done virtually. One of the things that happened during COVID is having to very quickly pivot to a virtual, but it turns out that there's some advantages to do that because more people can participate, and people who might not be able to easily travel can participate. Offices that are busy and it's hard to let somebody go for a week can have somebody participate part of their time. So there's a lot of experiments, and some of them have been going on for multiple years, both winter weather and flash flood and intense rainfall, and the various hazardous weather test beds have been going on for over a decade. Aviation Weather Service also, Aviation Weather Test Bed, also multiple years of weather experiments with airlines. Let's see, I want to keep going. One of the points I want to make is the testing and evaluation goes beyond quantitative. This often includes subjective evaluations by forecasters at the national and WFO level saying, I like that, I don't like that, I don't know how I would use that, I couldn't use that fast enough to do something, so we need to adapt so that I could use it. Focus groups, I don't think I actually have a next slide on that. Focus groups and integrating social, behavioral, and economic sciences, sometimes in a very formal way, and sometimes in a less formal way, but informed by how those sciences are done. And then often the results of other social science work being integrated in informing the work of the test beds. And this is a quote from Carley et al., that white paper, that feedback from test bed experiments has proven to be an effective strategy for model developers to build the annual development cycle of the next generation CAM system. So. Another thing I want to point out is that the test beds, the network of 13, engage many people. And so this is something that could contribute to and work with UFS and EPIC is The testbed community brings in something like over 500 individual a year into one or another kind of activities. So potential to use that to inform people about UFS and what the advance is. And that includes some of the traditional people like WFOs and other kinds of forecasters. Central Weather Service units are often involved in aviation weather activities in universities, but also broadcast meteorologists, airlines, National Energy Agency Fire Center, and a number of other agencies, sometimes international partners, North American Ice Services, and others. So a very wide range of people have some sort of connection to test beds over the course of a couple of years. Here's a few challenges, and I want to especially thank Jim for these. Collective data storage, like lots of times things are being stored in different places, but perhaps we can find some efficiencies in data storage. Collective ways of doing visualization. Some of this is already happening, but we could probably do more of it. Some of the things that we've heard about here already is the scheduling. This was in the session late yesterday afternoon. How do you avoid the fatigue of different people being pulled into multiple experiments or asking to do opportunities to be involved in multiple experiments, and having enough people to participate in all the different experiments across multiple test beds. Let's see, real world evaluations and tying the various evaluations all together like the RFS white paper did. And then how do we integrate the fast pace of AI/ML development into the test beds? This is part of that agility issue. How do we start bringing this in and take advantage of it? This is my last slide, just to emphasize that most of the test beds and proving grounds already have activities that are supporting UFS development. There's a few examples there. I've mentioned a couple of them, but I want to mention MJO teleconnections, diagnostics packages tailored for S2S, the MET Plus verification framework I mentioned, improving DA algorithms for, this is a COMT and a coastal thing, for ocean forecast systems, enhancement and development for operational products through utilization of the model suites. The excessive rainfall outlook is an example of that. I would also say WAFs and WAFcasts, and there are probably a number of others. And then we have capabilities that can directly support or benefit UFS, and some of those include the robust testing and evaluation projects, processes, access to forecasters, access to a whole variety of potential users. We're engaged with SBES, both implementing findings, so if somebody's done some social science and we use it to inform what we're doing, and then generating it in some cases. It's being funded and being actively done in test beds. And then just probabilistic products are really a major focus. There's very little that's being done that doesn't have an eye towards probabilistic. So I invite you to work with us and start talking to the test bed community early, and specifically to the test bed group involved in an NCEP center on whatever variables you're working on, so that we can think about what you're doing and when it might need to be tested, and talk to people like Jordan and Kevin on how we might work on that. So that's all. How are we doing on time? I'd like to call Chandra. You're in the room. Come on up. So what we wanted to do with this session is to really foster a dialogue with the panelists, both in the room, Kevin and Chandra, and on screen, Jim Nelson and Jake Carley. Could you go to the next slide so I can show who's, and Catherine, thank you. I knew there was one more person. So here are the panelists, and I want to haven't introduced yet Catherine Newman, who's the Science Deputy Director at the Joint Numerical Test Bed, and I want to both appreciate Catherine for jumping in at the last minute and acknowledging that Louisa Nance was one of the ringleaders for getting this session and was unable at the last minute to be here this week. So I'm ready to take some questions from the audience if you want to come up to one of the microphones. Good, I see somebody getting up. go ahead and get in line, please.
Yeah, thank you. Very good overview from everyone. And this is really where the rubber hits the road, and it's connecting that whole research community down to what ultimately goes in. More of a humorous point, I think. Your picture of the road trip, I think of, my kids. Are we there yet? Are we there yet? Actually, part of it's the journey. I mean, ultimately, we do need to get to go someplace, but the journey is what we have to work on to improve that whole R to O. The inception of an idea all the way down then to what goes into operations. So anyway, just a thought.
Any of the panelists want to comment on that?
Yeah, I agree with that. I mean, that's what JTTI did. Okay, can you hear me? So what JTTI did was, JTTI started funding projects at the readiness level 4. The 4 is where the concept is already found and then ready to be developed into an application. So when JTTI funded projects at readiness level 4, as soon as project is funded, JTTI, the PI is connected to a point of contact in the weather service. It's right at the beginning of the project. And then the PI and then point of contact are supposed to work on a transition plan at the beginning of the project itself. So the process of developing the transition plan, it takes like almost like 2 years. I mean, it took like more than 2 years sometimes, and then slowly we kind of reduced time to like 1 year, 1.5 years. So the process of developing a transition plan engages the PI and then the operational end user, basically. Okay, so that is how we connect these two people, and then by the time the project is completed, weather service or operational folks are fully aware of what this project is about, and of course it goes to the test bed, testing and evaluation stage. Even at that point also, the forecasters are invited to the test bed in the process of testing and evaluation. So the operational people are aware of what this product is. And then by the time the project is complete, I think the people in the weather service and the operational folks are fully aware of the benefits of the project. And then the transition becomes easier, a lot easier at that point. I think that's one of the things JTT has streamlined.
Let's get there. Yeah, Jim, go ahead, and then Steve.
Yeah, sure. Can you hear me well?
Yes.
All right, good. Thanks, Mike, for bringing up that topic. And just to elaborate a little bit more, I think, is it not only a journey, it's also a build-up through the journey. I like to use the analogy of a bridge between users, end users, stakeholders, and developers, modelers. And the first meeting that you have to cross a rope bridge. And then you then you build it over and over again, and it gets more and more stable. And you understand a little bit between each other. And therefore, when you're meeting across that bridge, it's actually pretty sturdy, and you know what each other wants and needs. And you're able to successfully get to a point where like Chandra said, or RL8, or what Jordan said, and you're ready to make sure you can make a successful transition to operations. I think it's a little bit more than just being in the car and riding along together. It's understanding each other and going back and forth in the communication between the end user or stakeholder and the developer slash modeler or NWP expert, just to make sure that we make it to that end. And we can find along the way. Not everything has to be successful. You find along the way that you're going down the wrong path and you start over again.
Could I just add one comment there too, another analogy? Sometimes the car runs out of gas before it gets to the bridge or on the bridge. And I think this happens maybe more often than we'd like. And so, we have to identify those projects that, maybe they're not meeting the performance through the test beds that's expected through the lifetime of the project. But we run out of resources, the project ends, and so we've got to be able to, maybe better recognize those projects that we need to continue and follow on.
Yeah, I just want to jump off on that too, because sometimes we're going to really beat this car thing to death, but sometimes the funding ends. Everybody's agreed that this is something we want to keep going, but before other funding is identified, the scientists have to go on to something else. They don't have funding, or the postdoc or the key person takes another job, or they get pulled into another project or something like that. And then even if it's a year later, it can be hard to restart. So I think it's really important that we look at those projects that are at a level where we want, whatever the readiness level is, it's like, this is good and we want to keep investing in this. And how do we make sure that we don't get tripped up, that we don't have, people have to move on to something else because they don't have funding. All right, are we done with that? Jordan, please.
Yeah, one other thing I wanted to add to that good analogy of the journey is that another thing that can happen is sometimes the destination can change. So you might be a year into a testbed project, and from another testbed project, there's been discoveries that there needs to be a big change to a model that you've proposed to make enhancements to, and then suddenly you find yourself what you thought was going to take 2 years, you might need 5 years, and you don't have that amount of money or time in that project to accomplish that goal. So suddenly your benchmark of, oh, we're going to get to RL7, it gets stalled at 6 now or 5. So there's not always a solid destination in the journey. Things can evolve year to year.
Well, and a corollary or that, or a different example of that is recently the Evaporative Demand Drought Index, which JTTI has funded. The National Water Center decided that that was no longer one of their priorities. So we ended up getting together and figuring out, and it is about to go operational at the Climate Prediction Center. So, yeah, but that took some pivoting, and the pivot also involved some more innovations on that. But I don't think we need to go into more detail on that. But sometimes the end goal changes because the priorities of the organization. Hey, Steve, I want to give you a chance. I think we've talked about this enough for the moment.
Yeah, I love how these R2O sessions just bring out the best metaphors. So, death to the funnel, okay? Death to the funnel.
That's not what I meant.
Well, I know, but it's weird how we get stuck into these analogies and they can lead us to better process or worse. So yeah, I'm not a fan of the funnel. We'll make this funnel-free R2O discussions henceforth. All in favor? Okay. Yeah, and on to the road trip. This is a great discussion. So the young scientists in the room, this is, to me, like one of the most takeaways from this conference. This is like one of the most important sessions because this is the best of NOAA, actually, but it's the most undervalued resource in all of NOAA, all the people and activities around this. This is what innovation happens in test beds. It's not like, oh, this great thing happened and now we're just going to work 24/7 to get it in operations. It's a long, twisted, nonlinear journey that has twists and turns and run out of gas and all that other stuff. So this is the messiness of R2O in all its glory and all its greatness. And I feel that along with the other challenges we face about science in general, and efficiencies, you can't rush this process. You can't bring something from idea to market to operations without, kicking the tires at a minimum and really road testing stuff and bringing it to stakeholders to see if the idea actually has the value that you thought it does. And if you rush to operations too soon, you're going to spend a lot of money for nothing. And we've seen that before. So I don't have a question here, but I've been sitting in R2O sessions for probably at least half my career, and I'm seeing a helpful evolution in the description here. So thanks to everyone who participates this and are hanging in, because this is where we take those ideas and we forge them into something meaningful and valuable. Thanks.
Thanks, Steve. Who else? Do we have anything online?
Hi. So maybe I'll just start with an anecdote of something recently. We had a land model developers meeting a few weeks ago, and I was giving a talk there. I decided to give the talk, put my UFS land working group hat on and give a talk on transitioning land model research into operations, because I feel like a lot of the good research that was being done, this meeting never makes it into the operational model. So one of the organizers of the event set me up perfectly a couple of days before I gave my talk by saying, we define success of our research by getting publications, right? And so my talk was essentially countering that by saying, we need to define the success of your research by getting it into operations. And I'm kind of wondering what the panel's thoughts are, people from like the program offices, like how do we change the attitude of the researchers to define their success of getting the code into operations? And I'm, thinking like it doesn't have to be RL 8 code that gets into these models. It can be RL 3-4 code. Speaking from like a coder's perspective, but anyway, just kind of wanted to hear the perspective of how we can change that attitude.
Comments?
I guess I could start. Yeah, I mean, defining success, it's different depending on the work that's being done. Success is sometimes failure. You try something new, it doesn't work, and you move on to some other solution. So that itself could be a success. Documenting new innovations that maybe are not prime for operations, but they've been prototyped. Maybe there's optimization that needs to happen. It's worthy of a publication to document, and someone else can take that on and transition it. That's a success. But yeah, I think ultimately from a weather service perspective, getting something in the operations is certainly maybe the pinnacle. So, but yeah, just to say that there are definitely various ways to define success, and it's maybe dependent on your objectives.
Yeah, and let me just add one more thing. I see a couple of their hands up, but just to comment off of something I think Jordan said earlier, that like, getting, having frequent interactions, I think what happens a lot of times is that it ends up being like 2 weeks to go in the project, and there's sort of we need to jam this thing into a repository somehow, and there isn't enough like interaction throughout the project, or maybe requirement to interact throughout the project to like do these things in small pieces.
So I think again, as Kevin said, success depends on how you look at the success. For example, earlier on, JTTF funded a project HARI. We were all thinking of operationalizing HARI, but then it didn't have enough value. So then we scrapped that, and then we started RRFS. But the funding, whatever we funded with HARI, the value we got out of it did not go waste. That information was used, that was informed to inform the formation of the RRFS. So it all depends on how you look at the success, basically. And another thing I want to point out was, because several things people pointed out to me early on, when JTTA was funding the projects, a lot of people were from the academic community especially. Because in the universities, they don't give a credit whether they're transitioning to operations or not. They only care about the project for publications, for their promotions. But then I made it a requirement that you have to transition to operations because this is the program funding. Transition is a requirement. So I think the academic institutions have to change how they promote their people, how they value, how they grade their professors, So they have to give credit to something. If a professor kind of worked on a project and transitioned the project to the operations, even though a publication did not come out of it, but then it is showing the value to the community. So they should include that in their grading and rating the professors. So that universities have to work on that one. So.
Anyone online?
Yeah, I have a few thoughts on this one. I'm Jacob Carley, Chief of the Engineering and Implementation Branch at the Environmental Modeling Center. Thanks, Mike, for the great question there. I think some of this boils down to incentive structures, which we've kind of, a variety of us have hit on a little bit. You know, if some of these awards, as Chandra was mentioning, can focus on deliverables being, you know, more operationally related as opposed to publications, or, you know, a combination of both, I think that helps. It's also mentioned that, you know, not everything should be transitioned to operations. You know, it's okay to fail. I think some degree of tolerance for that is perfectly okay, and in fact quite reasonable. And we have to be comfortable communicating that to the folks that are doing the work. I think it's not a failure if we learn something. I think that is overall a good outcome because we've improved our body of knowledge. I think one of the challenges also to getting something from the community into operations is having an appropriate landing space with attached resources. So from a modeling perspective or NWP perspective that I have sitting in my chair at EM, making contributions. But it becomes difficult for us to incorporate those contributions to the next version or the next release of a system if we don't have a mechanism in place to receive that and have it be resourced as well. Because there's still the extra mile or two that we have to do in terms of testing, validation, incorporation, and of course maintenance. So that's a little bit of a challenge. So it's where we see the most, I wouldn't say the most, but that's just one particular area where we do see a challenge of carrying things across that mission. And so the researchers could do everything they could do in their power, but if we don't have anything on the receiving end to catch the football, you know, it's fall, it's football season now. There's, you know, it's a little bit hard to carry things across. I'll stop there. I have a few other items I'd like to talk to you about the research transition process and the operational implementation process that I'd like to get to. But I see Jim's got his hand up, but I don't want to monopolize here, so I'll hand it over to Jim.
Okay, I just want to toss one other thing out, is that I think we often we don't track things after the grant is ended. So sometimes it takes months or longer in the next step. So I've sort of lost track. Jim, you have something to say about this? I want to put a pin in for Jacob to say a few things. Jim?
Yeah.
We've got about 20 more minutes.
One last thing, Jacob hit a lot of things that I wanted to bring up as well. But one last thing, I think the question of how do you make sure that you get the concentration off of publications? I think number one thing is what I see, even from the CI perspective, is that's the concentration of how they get promoted. And if we try to make sure that we realize that some of the things that they're doing from a CI perspective is operational aspects and may not lead to them having the time to make sure that they get a publication out of that. And I know it's part of the, you know, proposal aspects of getting a paper out of it, but if that's what we're worried about, then we're spending a little bit more time, a little bit less time making sure it transitions and trying to get that publication in before the money runs out. So I think if we have a different incentive, or there's multiple different incentives as far as promotion potential or raises, that should be part of the aspects of going forward, and try to de-emphasize the publication aspect of it. That's just one thing I see from my perspective.
Okay, I'm going to go back to the room. Mike, did you have something to follow up?
No, I just wanted to say during that talk, I did use the analogy of, you know, the car crossing the finish line versus getting stuck in the mud.
You know, this is funny because I started using the car because somebody said that the test beds were the express lane. And I'm like, sometimes, but I need something better. All right, Lisa, and then I'll come back to you because you've already talked.
I have,
And then Jacob.
I have a question to Kevin. Just to follow up on your mentioning of the UFSR tool project and expanding it to be more for the wider community. And as you mentioned, in the first six years, I guess we're coming into year 6, it's been a quite heavy lifting and heavy work for the research labs and NOAA EMC. And I was wondering if the thinking is that in the future there will be less resources for NOAA and NOAA research and NOAA EMC at the expense of expanding it to the community, or if you think that the pool is getting larger and there will be simply more research done. And also, if you have a comment on, when we work with the wider community, that often means that there's a lot of work for NOAA in porting workflows, supporting where data is located, helping with integration and, say, another physics suite and so on. Would that work be somehow funded or recognized, or is there a plan to acknowledging that takes a lot of effort and resources too?
Yeah, it's a great couple of questions. I think I can't really comment on the resources because, of course, year to year it's unknown. Priorities change. I'm hoping that modeling is becoming a higher priority in the next few years. So what I would say is, even if resources were level, they would be maybe distributed a bit differently and more targeted. The project has been very ambitious over the last several years, and I think it served a great purpose. So I think now we can pivot to looking at more, trying to solve more specific problems with our performance and skill of the models, and trying to prioritize that, and being a little bit more agile on who we can bring in to work with us as partners to solve those challenges. Could you repeat your second question? Sorry, I didn't quite understand.
Well, I guess my question is, because there is a significant amount of resources that goes into NOAA helping and supporting the community to be engaged in our modeling systems. I feel like that often falls between the cracks in a way, because it's hard to measure how much work that is beforehand. But I guess my question is if that's recognized by the program office, that there will be a need for that type of funding.
Yeah, I mean, I don't know if this addresses the question, but I know, we've relied on Epic a lot for sort of integrating new components or infrastructure, doing some maintenance optimization. There's, I think a big challenge is like the variety of HPC flavors that need to be supported, and always bringing in new systems that add, there are other things too on top of what you mentioned that add overhead, and we need to adequately resource that for sure. So.
Hey, Kevin, let me follow up on that with something that caught my ear when you were talking. You were saying that it must have been mostly static and who's been involved, and now that haven't had the agility, but you hope that going forward you can pursue some broader. What ways are you thinking of doing that?
Yeah, so I mean, we're just in initial thinking, and I think WPO hopefully remains a strong partner in these efforts, and we always have to sort of walk in lockstep for addressing priorities of the agency and making sure that we're on the same page and we're synergized and more efficient. So I don't know if your question is more like, how we do acquisitions and things, looking at notices like funding opportunities, if they're competitive, non-competitive contracts, or...
It was more like, more general, even like, what are ways of having more people to be involved? UFS, we've heard people say, is not a funding opportunity. So
right, yeah, I mean, I think the first step is for us to identify really what the major challenges are with the performance of our operational production suite. So maybe revisiting, like, we had in the past sort of this forecasters feedback workshop. I think that was a long time ago. I don't even know like how many systems have been upgraded to sort of revisit the, some of those metrics that that are underperforming. So I think that's really the first step, is to really identify where we need improvement, what are the priorities, and then looking for solutions. In terms of process, I'm not really sure how that will unfold, but
it starts with what are the challenges,
right.
And then there are various different ways that people could address those.
Exactly.
Yeah. Yep. So okay, Mike, is it quick? Go ahead.
Okay, I'll try. Mike.
And then we're going to Jacob.
Got it. Mike Barlage had asked about papers, and that's a metric. That may be true for academia, but I think the broader picture is educating our institutions to understand the impact of our work. And it's good to publish. And I know when I was at EMC, I wanted all the people working with me, hey, publish your work, that's good, but we want to also improve operations. So I think it's more of an institutional education. What is the impact of your work? That's key. That's critical. Jacob, you had said that not everything goes into operations. That's true. But I'm sure you would agree with every bit of research that NOAA funds needs to support the NOAA mission. And I will contend in one way or another, ultimately downstream, it should then help with operations or the things that come out of NOAA. So you want to do basic research? Go to NSF. Years ago, I was talking to a program manager who kind of said smugly, well, we're just like NSF. No, you're not. There's the NOAA mission, and that's what we support with our research. So just want to make sure that we don't forget that. So we should cooperate. There are things that NSF does, that NASA does, that DOE does, USGS, et cetera. And they need to all be integrated in some manner and understand what's going on. There's one Earth. There's not an NSF Earth. There's not a DOE Earth, et cetera. So, this is a plea to work together.
Good point. So, okay, Jacob, you had some things you wanted to bring up, and Jim may tag team on those.
Yeah. Thanks for that. Mike, I agree. We want things to support overall the NOAA mission. I same page. One thing I wanted to talk a little bit about, this gets back to some of the slides that Kevin showed earlier on, the transition to operations process. It's something I think that has a lot of room for improvement. And I think that over the next year or two, I'm hoping that we'll start to see some changes there, into moving from sort of this more, what I would call waterfall type approach, to something that's a little bit more agile and also respectful of how scientific progress and innovation proceeds at a nonlinear way, just the way that Steve was mentioning earlier. I think there are a lot of things that we can do in terms of the CI/CD space. So for those who don't know, continuous integration, continuous deployment or delivery. Some of those things are expanding unit testing, like we heard about on Tuesday from Alex and Marshall, but just overall improving our testing framework. And really what I'd like to get us toward is minimizing the differences that we have between our development or research environments and our operation environments. So this gets to the point about how we have many different R&D HPCs plus an operational HPC, and we want to run on the cloud too. And that's a lot of overhead there, and making sure that our codes are portable across all platforms, support multiple job schedulers, things like that. But at the end of the day, if with the goal that we have here is to transition the best stuff into operations, it has to work on the operational framework, right? But we don't want to be in a position where we're doing rework every time an innovation comes in. So an innovation comes in, we have to rewrite all the code, the scripts, everything to get it up to standards. It's extra work that's not ultimately necessary, and we can build steps into our process to ensure that we're more closely aligned between the development environment and the operational environment. So things like automatic code analyzers and checkers to when we're making pull requests in our repositories. It doesn't get in if it doesn't meet the standards, right? So in that way, you remove tension between people, with one person saying like, oh, no, being the gatekeeper and respect my authority and all that. And you make it automated and you make the machine make those judgments and those decisions. So you can kind of enforce a lot of that stuff along the way with some of these relatively straightforward practices that have been in the software engineering community for quite some time. To that point, we have some pretty exciting work going on with some agentic LLM type approaches to completely automate code compliance checking, or what's known in the EMC vernacular as EE2 standards, that can kind of read through the entire system code base, give you a full report on what is and is not within the standard and what needs to change and how it needs to change. It's very early days, but having access and support for these tools to do these kinds of activities will help minimize the difference between the developer and the operational environment, such that, you know, the terminology of crossing a valley of death or bridge or anything isn't really meaningful or doesn't mean a whole lot, because there's no bridge to cross. But the operations side of the house and the development side of the house are kind of coexisting together and helping inform how we want to do the development, how we want to architect things at a much earlier stage. This is going to work across the board, but I think over time, it's going to have a substantial improvement on how we do those R2O actions. The last thing I want to mention really quickly is that oftentimes when we do our operational implementations, we are thinking in terms of all the bits and pieces and scientific innovations we want to get into a version. But I'd like to ask everybody in the room, do you really know with a high degree of certainty when your scientific innovation is going to be complete and ready for prime time? Like, do you know what your experiment results are going to be before you get the results? Probably not, otherwise we wouldn't be doing the experiments, right? So when we tie those scientific innovations to specific schedules and calendar events, and we try to package everything together, well, what happens is, well, we need a little bit more time to test. These things aren't maybe turning out. We need to tune this, adjust this experiment, and so on, and then we push that implementation back. And what ends up happening is we get a lot of risk and a lot of things kind of coming together into a single implementation, and it's difficult to plan for. It's, you know, the scope is changing and all that. Instead, I think what we also need to do is move towards a paradigm or framework of where we're doing scheduled implementations, and we have a process where we pull in regularly what's ready from our scientific community and already well vetted, package that up, do final testing, beta testing, evaluations, and that sort of thing, and perform regularly scheduled implementations. So there's no more waiting a handful of years between implementations. They're coming at predetermined schedules. Everyone knows when they're coming, and all the scientists and developers know when their stuff needs to be ready based on the calendar. And if it's not ready, we know the next time that they'll have that opportunity to get that information packaged in together. And I think that would also help us interact directly with the wider community as well, because they would all know and be able to predict when these timelines are kind of coming up and when these important events are happening.
We got 3 minutes.
That's a great point. Yeah, so I have about 3 people, so thank you, Jacob. I'm gonna next.
I'm Rusty Benson from GFDL. One of the things I wanted to point out, and I think I heard Jacob mention this earlier, and I think it goes to what Lisa was saying, is that you know, we're doing a great job of building the UFS, building it, but we're at a point of maturity where if R2O is saying that something is not acceptable or may never be acceptable for operations, there needs to be a pairing process. We need to start, you know, reducing the scope, or not the scope, but the number of options that we have in the UFS code to keep it agile, to keep us going forward, and to make these transitions or make these tests go quicker and be more meaningful for the community, so that the UFS just doesn't continue to grow like the social network diagram where we just keep having branches going.
So here's what I'm going to do. Instead of letting them respond, I'm going to let the last 2 of you make your comment, and then there can be discussion in the room. So just go ahead and make question or comment, and then I'm going to have you.
Yeah, so I represent the academia in this room, and since there were comments that the academia has pressure to publish, whereas the operations do not have any requirements like that, I would like to mention that all other peer operational centers do have great science publications coming out of their centers. The scientists that work there, they publish. So, and we know that their models are great. So publishing doesn't mean that you spend less time working on the implementation. Even the people writing code and developing the models, they are scientists, so they do like to do a little bit of science. So I think it will be great for them if they also have this chance to do some science. And then we heard Jacob talking about implementing new science, and the new science is vetted in publications. So if we don't publish this new science, I don't think that it's the greatest science that we will bring to EMC for implementation, to operations for implementation. So.
We're at
Okay.
time.
Did someone have a comment on that? No. All right, I'm going to let Jan.
We're at time.
Can I just let him make his statement? Go ahead.
Yeah, so it's just a quick question from online. I'll just pose this and maybe there's a quick answer. Who, NSF or NOAA, should fund RL2 or 3 research of using AI ML to improve data assimilation as shown in yesterday's NOAA Eagle Talk?
All right, we'll just let that, they want to finish, so we'll put that, I just wanted to get that out there for discussion in the room. All right. Thank you, everyone.
Yeah, feel free to applaud. All right, yeah, thanks to our panelists and to Andrea Ray for a wonderful session there. Next, we're going to move on to Shastri Paturi with the Navy to talk about their coupled sea ice ocean atmosphere model. So, well, I'm on the screen now. Is Shastri here or online?
I'm online.
All right, so if we want to...
Can you hear me?
Yes, we can hear you just fine. Get the screen sharing set up.
Yeah, unfortunately, I'm in a skiff location, so I won't be able to have my video on.
That is just fine. Do you have a presentation to share?
Yes, I'm going to share my screen now.
All right, I'll let you
Can
take
you
it
see
from
my
here.
screen?
Absolutely.
Okay. 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 Oh, my name is Shastri Paturi, and I work at the Fleet Numerical
Apologies,
Metrology and
we
Oceanography Center.
see your slide deck. Can you go full screen on the slides?
I
Try
am... Okay. 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 Can you see it now?
We still see your slide deck, but I think you can just go ahead.
Okay. When I move my slides, can you see the slides moving?
No, we see your slide deck, and if you like, we can share for you as well. Just tell us when to advance them.
Okay, I did, okay, I need to, because I have added a couple of images, animations, so the one on the, yeah, it should be fine. Yeah, if you can share the screen, that should be fine. Yeah. Okay, I stopped sharing.
Give us a moment.
Mm-hmm. Yeah, if you could share the PDF, sorry, the PowerPoint, that should be fine.
Yes, it's right up here, and just tell us when to advance.
Oh, okay. Yeah. Yeah, my name is Shastri Paturi, and I work at the U.S. Navy's Fleet Numerical Metrology and Oceanography Center in Stennis, Mississippi. And so FinMark is actually the center that research laboratory, Monterey and Stennis in operation. So my talk on the overview and future developments of the U.S. Navy's Earth System Prediction Capability, or ESPC in short, is the work done by all the authors that I have listed here with me. just presenting the work done by them, and this is the model that is being run operationally at um, um, by Finmark at Stennis. Next slide, please. Okay. The U.S. Navy's ESPC is a global coupled system with two-way coupling for the atmosphere, ocean, and size. With NavGem being the atmospheric model, and for ocean it's HICOM, and for ice it is the Los Alamos size model. And all three are coupled through the SMF NUOPC coupler. Um, the, um, uh, the, the ESPC, the first version of the ensemble became operational at Finmark in August of 2020, and the products are being used by the Joint Typhoon Warning Center for their tropical cyclone genesis and prediction. And the ice products are used by the U.S. National Ice Center for their polar exercise, resupply mission planning, and for iceberg forecasting. And apart f- so Finmark runs the two versions of the ESPC operationally, the one the ensemble version and the other deterministic version. So the deterministic version got two became operational in August of 2024, and this version 2 of the deterministic had the Waywatch 3 coupled only one way. So all the three components for the atmosphere, ocean, and sea ice have the data assimilation included, and it's a weakly coupled DA system. Next slide, please. So this slide highlights the upgrades that went into the ensemble from version 1 to version 2. So in the ensemble, the ocean tides are included, and the top left plot shows the M to barotropic tidal amplitude and the constant phase. And on the right, top right is the Wavewatch 3 output of the significant wave height for 4 or 5 days, the progression of the wave spectra. And as I mentioned earlier, it is currently only one-way coupled. And also the version 2 of the ESPC includes an extension in NavGem to extend up to 110 kilometers. That includes the middle atmosphere. Next slide, please. So this slide has all the information related to the configuration of the different models, and the upgrades between version 1 and version 2. So the ESPC ensemble version 1 uh, ran for 45 runs for 45 days, and the version 2 also is the same. But as I mentioned, the atmospheric navgem has higher horizontal and vertical resolution, which includes the extension up to 110 kilometers at the top layer. That includes the middle atmosphere. And for the deterministic version 2, the forecasts are run for 16 days. um, uh, the U.S. Navy is the only center that has um, a very high resolution ocean and sea ice model, which is 125th degree in horizontal resolution, and that includes the tides along with the version 2 that is being developed right now. And the and the upgrade between Ensemble version 1 to version 2 is the change in the version of size from 4 to 6. So 6 has more ICE categories to more ICE categories included, and also the version 2 includes the Arctic landfast sea ice. The Wavewatch 3 is at a quarter degree for the ensemble, but it's 1/8 degree. In the deterministic version, and a land surface model is embedded within within navjam, and we also have an aerosol component which is also included with navjam for version 2. Next slide, please. One of the reasons for having the uniqueness, high resolution ocean and sea ice is the uniqueness of Navy's ESPC, and the U.S. Navy requires high fidelity simulations in the atmosphere, ocean, and sea ice that is used for operational preparedness, force positioning, and for other um, and for other um, for other other products used by the fleet. And the animation on the left is for salinity for 45 days, and it shows clearly how the eddies are resolved with the high resolution ocean model. The center plot shows how these products will be used for the Arctic shipping routes, not just for the Navy, but also by the other centers, which gives information on the sea ice extent, which is very important for determining the ice edge. And also these products are also used for the biogeochemical modeling, and also for determining the location of the oil spills if they occur. Next slide, please. Another reason for having a very high resolution is to um, uh, i- um, um, is to resolve the internal tides, and the addition of the astronomical tidal forcing generates the gravity waves at tidal frequencies, uh, and the two animations on the right, which includes one for the temperature on the top panel and salinity on the bottom panel, shows the evolution of the internal tides when they interact with the bathymetric features, and these products are very important uh, mm, for the military, and also helps in generating the acoustic parameters, which are also very important. And the location of um, um, this animation is between the Philippines and Taiwan, as shown on the left panel. Next slide, please. Also with the high resolution ICE component that is included with the ESPC, and this is from the deterministic version 2, is the location of the ice fractures, which are represented by the lead area opening rate as a percentage, and this and these this information more or less shows where the leads uh, are more likely to be present, and not for like identifying them. But these are very important and are used by the US snake for their polar experiments, and also for locating the also for iceberg location forecasting. Next slide, please. The this um, The output of the ESPC deterministic version 2 is compared against the standalone systems to determine its fidelity for improving the forecast on which the US Navy depends a lot. So on the left panel is a comparison of ESPC against the standalone NavGem, which shows the temperature bias as compared to the radiosondes for for 5 days. And it can be seen that the biases became smaller in the middle atmosphere and in the troposphere with ESPC as compared to the standalone NavGem. And this can be attributed to the better physics that is included in the NavGem as part of the ESPC. And in the middle panel is a comparison of the upper ocean currents vector correlation plot between the version 2 ESPC compared against the GOFS 3.5, which has been retired long. And this plot shows that the ESPCD version 2 outperforms the standalone GOFS, not only for this for metric, but for most of the metrics, if not all, that are not shown here at this moment. And on the right hand side is a comparison of the WaveWatch 3 significant wave height compared against the standalone WaveWatch 3. So for all the three statistical parameters that were looked into, including correlation bias and the root mean squared error, the ESPCD has a significant improvement in reducing the bias. It also has improved in correlation and RMSE, but the significant impact is on the reduction of the bias. Next slide, please. Okay, so this plot shows the continuous rank probability score, which is a probabilistic error score for the atmosphere. And this is for the comparison between the ensemble version 1 and version 2 for the 5 parameters listed on the x-axis, which includes the temperature at 2 meters, 850 hectopascals, and others. And this is for all the 45 days for which it was run. So the green circle shows the maximum of 20% of the difference in the CRPS between version 2 and version 1, where the green circles show that the version 2 is better than version 1, and the bigger the size means the version 2 performs better in this score for the ensemble version of 2. And um, the purple color shows that the version 1 is better, which is which are like for very small instances, and the gray shows that it is statistically significant. And uh, overall, the relative improvements is largest for the tropical 500 hectopascal height, and the southern extratropical 2 meters 2 meter temperatures. Next slide, please. Okay, so here is a comparison of the Madden-Julian oscillation, which is a very important prediction for the extended range, and also used in the tropics for the tropical cyclone and tropical cyclone analysis. And the here, I mean, the ESPC version 2 is not has not outperformed the version 1 in many aspects, and this is one of them, where the version 2 is seen to outperform the for MJO based on the autocorrelation, the RMSE, and the ensemble spread error, like a plot shown on the right, in comparison to the version 1, the deterministic, as well as the ECMWF and NCEPS, the CFS V2, and the UK Met Office. So overall, I mean, all the models seem to be significantly underdispersive in comparison to the ECMWF, but the efforts are ongoing to address this error, and also by enhancing the ensemble spread in version 2. Next slide, please. Um, the temperature and salinity biases and RMSE for a single ensemble forecast are compared at depth, and the plots show the plots show on the left that the temperature and salinity biases are improved at depths less than 150 meter, but they get worse deeper than 300 meters, and the temperature root mean squared error is very comparable near the surface, but at all levels deeper than 50 meters, it gets more improved, and the salinity root mean squared error has shown improvement for depths less than 200 meters and comparable below that. So overall, the comparisons, the results for the temperature and salinity biases and RMSE are comparable between version 1 in comparison to version 1, but more improvements are expected before the model is transitioned to operations. Okay, next slide, please. Okay, so this comparison is also done for the Arctic sea ice drift, and the anomaly correlation and biases plots are shown on the left and the right panel. The ice drift correlation are very similar between version 1 and version 2, but there seems to be a little bit more bias for in version 2 as comparison to version 1, and investigate and work is being continued to determine what is causing this bias, which was found to be not consistent with the wind speed biases, which are not shown here, and also the ice edge errors are found to be larger in version 2 than in version 1. Next slide, please. The integrated ice edge error was also compared for the Arctic and the Antarctic region, and the US NICS marginal ice zone analysis was used, and for this comparison, and the US NICS marginal ice zone analysis is based on multi-source imagery from different satellites, and it's a very good predictor for how the integrated ice edge error is progressing over time. from the forecast for the 45-day forecast. And the plots here show that the that in version 2 the overpredicted regions are larger than in version 1, while it's opposite in the underpredicted regions. Overall, the total ice edge seems to be higher in version 2 than in version 1. And again, work is ongoing to understand and mitigate the source of this faster error growth in version 2. Next slide, please. Okay. Um, uh, there are there are many products which are generated by ESPC at the U.S. Navy and are disseminated to to customers within the U.S. Navy and outside. So one of them is the real-time multivariate MGO forecast forecast product, which is based on the OLR and the 850 hectopascal and the 200 hectopascal equatorial zonal winds. And the phase numbers represented by 1 to 8 indicate approximate location of enhanced convection. And also the wind shear anomaly product is also shown in the lower left panel. So overall, the MJO, which is again a large-scale tropical environment indicator, and a wind shear that is produced operationally, are sent to the JT WC, or the Joint Typhoon Warfare Center, Weather Center, and for their extended range tropical cyclone genesis and prediction. And on the top right hand corner, the plot shows the correlation between the deterministic and the version 1 control runs, and the result shows that there is a slight improvement in the Madden-Julian oscillation performance in the version 2 deterministic. Next slide, please. Okay.
3 minutes.
So yeah, so so this also this slide shows the other Navy ESPC products which are sent to the fleet. And again, MJO and tropical anomaly graphics are used by the JTWC for their 2 to 3 week tropical cyclone genesis forecast. The MGO graphics are also used to train students for warfare tactics by the Naval Information Warfighting Development Center, the Naval Air Warfare Center, Aircraft Division, also pulls these ensemble data for their anti-submarine warfare planning. And one of the biggest users of uses this forecast to help them with their biennial ice exercise and other missions that I had mentioned about ice work forecasting and stuff like that. And we also produce acoustic products which are primarily used by the fleet. And there are many other customers which use the other physiological parameter products as well. So in summary, the Navy ESPC version 1 was operational in 2020 and runs weekly with a 16-member system 60-member ensembles for 45 days. And the upgrades with the version 2 includes a one-way coupling to the ocean wave, extension of the atmosphere to atmosphere vertical layer to include the middle atmosphere, internal tides, and also the Arctic landfast ice. As part of the version 2, the deterministic version went operational in 2024, August of 2024, and is now producing output for 16 days. The version 2 validation is nearly complete and is actually completed, and the transitions to operations is underway, and overall it based on the metrics other than sea ice, the version 2 is comparable or better than version 1. So the other big upgrades include okay. Yeah, just one sentence and I'll be done. And the next upgrade includes the two-way coupling to the WaveWatch 3 and also the data assimilation component for the WaveWatch 3, and the upgrade of the atmosphere to to Neptune. Thank you.
All right, and we do not have time for questions, so you can ask them online and they can be answered in the chat. Our next presenter is Pedro Jimenez, who is going to be talking about the community-based fire model within the UFS.
Thank you. So yeah, I'm going to provide an overview of our development of a fire behavior model and coupling with UFS. I would like to thank first my collaborators, Maciej Dami, Maria Frediani, Daniel Rosen, Michael Kabulich, Catherine Wilson, and Rose Olsen. And also, they have been involved in development, the model and testing. But also, I would like to thank collaborators from NOAA, Ravana Madov and Sudhi Pihimiriti, that they have been helping with technical advice in developing the model. This is the motivation for developing the model for UFS. Wildland fires produce large socioeconomic impacts, and accurate predictions of the fire spread can aid decision makers in mitigating these impacts. Fire behavior models that account for the fire atmospheric feedback can provide predictions in real time, and this can help mitigate some of the adverse impacts. And the coupled model also can be used for research in fire-weather interaction. UFS was lacking a fire behavior model, so we've been developing, or we are in the process of developing a fire behavior model that we refer to as the community fire behavior model, that is based, closely follows world fire and coupled to UFS. This is how the world fire model works. First, we need to have a method to track the location of the fire front, where the fire is located, and we do that using the level set methods, which is a consolidated methodology to track the location of interfaces. It requires solving a partial differential equation, and it helps us, again, to determine where the fire front is located. Then we need to know how the fire front is advancing, and that's parameterized, and we need to know the rate of spread, which is a function of fuel characteristics, such as fuel characteristics, elevation, and near-surface atmospheric variables. So we know where the fire front is located, we know how it's advancing, so we advance, move on the front, and at the advance of this front, we ignite new grid cells, and the heat release, moisture release, and smoke production is parameterized as well. this feedback the atmosphere and changes the winds and the near surface atmospheric variables. And in this way, we have the coupling between the fire and the atmosphere. How does it work? This animation, somebody can help me to play the animation. When the animation starts, it will show a simulation with the fire atmosphere interaction. It will show the progression of the fire, and you will see the smoke. And it's not working, but it should have shown at the beginning how the smoke was interacting and reaching higher levels at the atmosphere, and towards the afternoon, the smoke was confined to a thinner layer near the surface, illustrating that the coupling of the feedbacks between the atmosphere and the fire. Isn't it possible to, somebody can help me to activate the animation? I think by clicking in play, it will show the animation. In the bottom left corner. That's it, here it is. This is what I was describing. Here you see the smoke reaching at higher levels of the atmosphere. We are transitioning towards the end of the afternoon. The atmosphere is becoming more stable, and you see the smoke that is confined to thinner levels near the surface. So how does it work? How good it is, the simulation? You can see here on the right the comparison of the simulated area in blue and the observed burn region, which is in orange. And for this case, you see good agreement between the two. This is expected because it was an easy case. The fields were homogeneous, the winds were homogeneous, but still it's reconforting to see that the model is able to reproduce this case. That was the starting point for our development. That was WordFire, and we developed the community fire behavior model to provide a fire behavior model to UFS, and it's based on WordFire version 4.33. We closely follow the methods in that version of the model, so we can compare the two and check for the consistency, adequacy of our implementation, as you will see later. The coupling with the atmosphere is done via the ESMF library, and this requires having a fire behavior model implemented as a national unified operational prediction capability, NUOPSI. And an overview of what it means is we need to have subroutines to initialize and advance the fire behavior model. And then these subroutines are called or are used in a lightweight file that is the CAP, the NUOPSI CAP, that also defines the grid and the variables that can be imported and exported by this particular NUOPSI. So the NUOPSI put the code of a component in a sandbox, if you want, and they interact with this CAP. And this allows for coordination and advancing different components when you wrap it with the ESMF library. The model can run offline using reading the atmospheric stain from an existing simulation, from WRF in this case, and we did this for testing the adequacy of our implementation, but it's proven useful to do some sensitivity experiments and do some checks and developments. And it can also run online, and this is the most important part, and it can be coupled to an atmospheric host like FB3 in UFS. We also have it coupled to WordFile, and I will show a little bit of that later. And we have also a capability to perform idealized simulations configured via the name list. This is how we have reorganized the WordFire code. We have removed some atmospheric dependencies that were within the fire code. WRF is an atmospheric model, so we have to do some cleaning there. We have to also do some reorganization of the code to create the standalone model, and we took the opportunity also to clarify the logic of what is being done. Here we are creating these advanced and initialized routines. we took also the opportunity to improve some coding of the code of the model, like imposing consistent formats across modules and other desirable characteristics in the code. Some of the processes are implemented as parameterizations that are controlled via the FHIR name list, and these parameterizations so far include the rate of spread, the fuel model, and the fuel moisture model. And the way we have implemented is we have defined abstract derived types in the code, and this is generic and provides impose the methods that any parameterization must have, and then when we create a new parameterization, it has to use these methods. And these are the parameterizations that we think there is room for improvement in the future. So we're expecting to improve them later. The code is self-documented. We believe that writing good code will provide the best information of what the model is doing. And we have recently implemented the parallelization. Parallelization is OpenMP parallelization. This was the first easier step to have the code parallelized, and MPI should follow. The code conforms to the Fortran 2008 standard, and we have an expensive automatic test available that they run really fast, 30 seconds or 1 minute, and it can help one when doing development that at least to avoid the most important bugs. The codes these tests are also run in regression test in the Git repository. It's already publicly available, the repository, and these tests are triggered upon pull request, and we have also we trigger this test during the night to make sure everything is going smooth. This is an overview of how is it implemented in the coupling. And okay, so on the right you see a very simplified version of the UFS. You see different NUOPSI components, the atmosphere, the ocean. UFS is much bigger, as you have seen in previous presentations, but this is to highlight the coupling with the fire behavior model on the bottom left. You see the two NUOPSI components, the UFS atmosphere FV3 and the community fire behavior model NUOPSI. And you can see the arrows that illustrate the exchange of variables between the two components. The heat and moisture and smoke fluxes from the fire behavior into the atmosphere, and the near surface variables coming into the fire model from the atmosphere. On the top left, you see a zooming in of this component on the right. And if you look at the fire NUOPSI, you see on the left that it requires input, external input. And there is only one requirement, which is a static file that defines the grid, the location of the region where we are simulating the fire evolution. This doesn't need to match with the atmospheric region, and the grid refinement, it can be independent of the atmospheric grid. Once we have this file, this fits into the fire behavior model, and here on the right you see different directories that we have in the code. You see the driver directory. This is where we have the initialize and advanced subroutine that I mentioned before. There is a shared directory with miscellaneous of subroutines that are used by different directories. Here is where we define our abstract derived types for the parameterizations. There is a directory that takes care of the input and output, the state directory where we define all the variables of the fire state. And finally, there is the physics directory where we have the methods to take care of the fire evolution and the fire physics. And this is where most of the methods from warfare are located. At the bottom, you see a little bit more details of the structure of the code. So on the left is what I described already, the ESMF code. This nuopsi cap is located here in a directory called nuopsi in the middle. And then on the right, you see other directories. Some of them take care of the automatic compilation with CMake, which is a standard in UFS. And there is another directory with the tests. Here you can go inside for examples of the fire name list and to run the test while doing some development. And finally, this is a file, the compile.sh script that you can use to compile the code. So this is an overview of the code. I have some slides to illustrate how does it work and to highlight the adequacy of the implementation and the consistency with warfare, which is the model that we closely follow in this original implementation. This is an idealized simulation, and this is an example of one way to ignite fires. It's a line ignition. You see it on the left. The fire started there. And the fuels are homogeneous, winds are homogeneous. So after running the model for a certain amount of time, winds are coming here from the left. So the fire is propagating to the right. And after finishing the simulation, the theoretical solution is highlighted there with that dashed black lines. That's where the fire location should be at the end. And what you see here are in the different colors are the location of the fire or the burnt area for using different methods, numerical methods to resolve the level set equation, the partial differential equation. And what I want to highlight is that when we improve the accuracy of these methods, we get closer and closer to the theoretical solution. We did this with WordFire back on the days, and we see here that we are able to reproduce these results, which make us believe that we are in the right track, or we didn't make gross mistakes in the implementation of the community-5 behavior model. This is a more challenging simulation. This is a real simulation starting as a point ignition where the start is located, and you see the evolution of the fire perimeter. And what we are looking in this simulation is consistency between the different simulations, because one is with UFS in blue, the other is with warfire in black, but we configure the models with the same parameterization, the same data to generate the initial and boundary conditions. So we'll be expecting to have resemblances between the different simulations. And in green is the simulation where we use the community-5 behavior driven by offline work data. And this consistency is what you see here. In the simulation, there are some differences because obviously the parameterizations, they are not the same and there are non-linearities, but you see the overall good agreement between all of them. This is highlighted on the left. On the top left, you see the evolution of the burn area, and you see that it's in agreement between WRF and UFS. And this is obviously because you can see at the bottom left, we have similar winds in the two models as a result of the similar configuration. This illustrates that also there is consistency between the fluxes that are generated by WRF and UFS. And you can see in the left the heat flux, in the middle the moisture flux from the fire, and on the right the smoke flux. And you can see how the blue line from UFS and the black from warfire, they are similar. You see different peaks at different times. This is because there are different timing in the evolution of the fire, but again, highlight the good resemblance between the two models. This is checking the feedback to the atmosphere. Again, we see consistency. So here we are on the left, we see the impact of these fluxes, in this case, the heat flux, in the temperature. And you see that on the left that these red grid cells indicate that there is a warming. And on the left is WRF, and on the right is for UFS. And you can see that they have similar location and similar magnitude of the heating of the atmosphere. And again, this is to check for consistency between the two models, because that's what we have been, what we will be expecting because of this configuration. This is another way to ignite fires, also checking again for consistency between the models. And we initialize the fire starting from a fire perimeter. There are two of these simulations, on the left and on the right. We start from the perimeter highlighted in gray, and we let it go the simulations. We start to simulate the fire evolution, and we stop when we have another fire perimeter available, which is in red. So at the end of the simulation, we will have expected agreement with the red perimeter if the simulation is perfect. What you see here is, well, this is not the case, but you see consistency between the different simulations. UFS is in blue, and WRF is in black, and the CAVN offline is in green. And this is especially the case in the simulation on the right. There is a really good agreement between the different simulations. That, again, highlights the consistency and the adequacy of the implementation of the UFS fire model. On the left, you see something that we need to improve. There are some regions in the perimeter that they are not active. The red and the gray line are matching, but we see that the model is evolving because we don't have a way to or impose that the perimeter is not active. But in the two locations where the fire grown, we see good agreement or the evolution of the fire. This is not the case on the right. If you look on the right, you see that we are underestimating the fire spread, and this means that there is room for improvement in what we have right now, which are the methods from WRF fire. So we are working to take it to another level. This is an example of the developments that we are working on right now, that we tried. Very briefly, on the top left, this is the impact of the fuel moisture content on the fire spread. And this is a diagram where we are comparing the agreement in the burnt area, and perfect agreement between the observation and simulations will have the different symbols on the top right and the one. And the different colors represent different fires. There are two simulations per fire. The first one starts with a fuel moisture content of 8%, the triangles, and the second one we impose the observed fuel moisture content that we were able to retrieve from satellites. And what you can see is that in general, we tend to go in the right direction. This is not always the case, so the experiment is not conclusive in the value of the fuel moisture content. But what I want to highlight is that this simulation, we impose the height of the winds that we are using to drive the fire, 0.5 meter, and this is a subjective decision. If we go higher to 1 meter or 2, we change results, and what we did, which brings me to my second bullet point there, is that we developed the model to use wind adjustment factors, and this height of the winds is determined by the fuels. This is a standard practice, but it was not available in WRF fire, but we have now in the community fire behavior model, and that's in UFS. We also have introduced calculation of the smoke optical depth, similar to RRFS, and here I should thank Ravana Bandov and Eric James from NOAA. With this development, there is an example here on the right of the AOD from a simulation, this one with WRF. And we also have a first implementation of the modulation of the fire emissions with as a function of the fuel moisture content. And this is ongoing work and collaboration with Wen Fu Tan from NCAR, from ACOM, the chemistry laboratory. And what we are working now is to improve the accuracy of the level set method in tracking the location of the fire perimeter. We have noticed that there are some instabilities in the location of the fire front generated by solving the partial differential equation of the level set. And we want to refine that to avoid these instabilities, and we are working on that. We also, as I mentioned, we have the community fire behavior model. We couple it to WRF as well, and this is to this was possible because the modularity, the initialize and advanced routines, and this is again a consistency check between work fire and work with the community fire behavior model that after 26 hours of simulation shows good consistency between the simulations. Again, this points us to the adequacy of our implementation. So why we coupled the model to WRF? Well, we had the vision with the community fire behavior model is to make it available to a variety of hosts and foster collaborative developments in order to increase our fundamental understanding of fire science and overall minimize the adverse impacts of the wildland fires. This is, we have been already coupled to UIFCW25 and to WRF, as you have seen, and in the future it should be relatively straightforward to couple it to MPAS once it's available in UIFS and thus having the NUAPC component. The model it can be run from the short-range weather application, and this is possible, make it possible to automatically simulate the fire evolution. The short weather range app generates the name list for us, and you'll see in a moment how this is done. And this provides an easy interface for running experiments and a new capability for UFS, for science and research. It provides support in multiple platforms, and it gives the UFS fire community access to all the extended capabilities of the short-range weather app. And we are able to reach a wider audience of users because the simulation of the fire evolution is automatic with this application. We have also documentation. Here on the top, you see the link to go to the documentation, and I'm going to highlight quickly, because I'm running out of time some aspects. The first one is how to configure the model. So the only thing that we need to generate externally is this file that defines the fire grid and two parameters, the fuels, which is like a land use that it tells the model where if there is grass, shrubs, or trees. And the second is the elevation in the fire grid. We do that using the WRF preprocessing system, WPS. And here in the documentation, there is a link to the information. It's all documented via the WRF websites. This is the only file that we need. And then we can use the short-range weather app, and also the documentation provides information. On the right is how you have to compile the short weather range app to take advantage of this functionality to be able to simulate fire, the fire evolution. And on the left is how you need to edit the config yarn file or UFS to activate the fire and the different options that we need to add. So the short weather range app is able to automatically generate the name list for us and being able to do the simulation. This brings me to the conclusions. We have developed and coupled a fire behavior model CFBN2F to UFS. The code is already publicly available in the different UFS repositories, the community UFS models, the short weather range app, CCPP, and maybe I'm missing one or two. We have seen consistency between UFS and WRF. This is that was our target because we closely follow WRF methods on purpose to check the adequacy of our implementation. And we are now able to take it to the next level. And we can run the simulation with the short-range weather app. The documentation is available to activate the fire model in UFS, and again, we are working now on taking the WordFire methods to the next level and improve the simulations. Thank you. I'll take questions.
Hi, Pedro. This is really exciting. It's great to see this coming to fruition. My question is, what's the readiness to take this to the next level? So if you really want to use this, say, in real time, what else do we need to do? And so one thing is, how much of a high resolution does the atmospheric model need to have, and what do you see the readiness of the UFS for that? Do we need to have 1 kilometer, sub-kilometer? And what is the readiness of putting real-time fire information through pre-processing system to be used by the fire model?
So the resolution, obviously, as higher you have it, the better. But that's not the case for, that depends also in the type of fire. There are wind-driven fires and there are more thermally driven fires. Wind-driven fires you can get by probably with coarser resolution, and we've done simulations in pushing the limits of UFS, I guess, 1 kilometer or so, and you don't see much of the fire impact for these wind-driven cases. You do want to go to finer resolution, LES-type resolutions, to get more advantage of the fire atmosphere interactions. UFS is not there, but I think is getting there. MPAS is getting there, and once MPAS is available in UFS, that may be the way to go with the final resolutions. We don't have yet the parallelization pushed into the repositories. We are working, as we talk, on pushing that. That's one thing that we need to have to make it into operations. The other is these little instabilities that I was mentioning. If you don't want that in operations, we should be able to resolve them. I think we have narrowed down what is happening, and it's already in WordFire. But I think that one we should be able to resolve it in the next months. The other one that it gives you room for playing there is which region do you want to simulate your fire? Do you want to simulate, for example, in the simulation I saw is one given fire. Say, hey, I want to simulate it here. We generate our grid for that region, and we simulate it there. Do we want to go like that, or do we want to go to a wider region where we have many fires and the different, probably the second option. The model it may need the MPI parallelization to go to a really big region, and there are other things that we may need to resolve to be able to make it happen to go to that really big region. That's my first thought, Elijah.
If we could get a round of applause for that presentation. And so I have a few announcements moving into our next session. So the next session will be our poster session until noon. So there will be posters both on the first floor and on the second floor catwalk. And that'll be a great time to chat with our poster presenters. Additionally, after lunch, we will be splitting into 3 different breakout sessions, one in each of these 3 different bays. In the North Bay will be the UFS application, Coastal Marine and Ocean Ecology. In the Center Bay will be the UFS application, SRW, RRFS, and MPAS. And in the South Bay will be the UFS application for AQI, atmospheric composition, and aerosols. So there's that. One more announcement, which will be that during the poster session, Jen and I will be going around interviewing people for a social media spot. So if you would like to be a part of that, we will be around. So thank you all very much, and enjoy the poster session.
Test, test.
Nice to meet you, Ramon.
I'll help facilitate the session.
Sounds good. Yeah, and I'll handle the timing and everything.
Okay.
Make sure. So, cool. All right, well, I'll just get started. So welcome everyone, just to make sure you are in fact in the right room. This is the parallel session for the SRW, RFS, and MPAS. Just to give a quick brief weather update, because I have 1 minute before we actually need to start. There are storms forming over the mountains, and there is a severe thunderstorm warning to our west for 1-inch hail and 60-mile-per-hour winds. So, brief weather update. And with that, I will introduce Curtis Alexander, who's going to be our moderator for this session. And I will note, I will be keeping time for this session. And again, if I cut you off, it's not personal. We just need to make an agenda. So, all right, thank you.
Thanks a lot. Welcome everyone to the session. We'll get started here right away. We've got 6 presentations, each maximum of 15 minutes, less if the speaker wants to invite questions and discussion. And then we're going to have about a 30-minute discussion panel in the last 30 minutes of this 2-hour period, and we'll get into the details there later. But without further ado, I want to get our presentation started. Again, Curtis Alexander, performing duties for Director of Global Systems Lab, and I'm going to turn it over to one of my colleagues. This is Matt Pyle at EMC, or maybe now MDC, to talk about the Rapid Refresh Forecast System version 1. So Matt, can you hear us?
Yes, can you hear me?
Yes.
Okay, great.
Take it away.
All right, we'll see how I do with Zoom. But firstly, I want to acknowledge my co-authors, which I like to call the rest of the RFS leadership team, sort of divided between EMC and GSL. The RFS has been under development for many years, and this development has been a hugely collaborative effort, say mainly between EMC and GSL, but with a lot of help, financial, scientific, and otherwise, from various agencies that are kind of listed below. Okay, so what is the RFS? The first, as a UFS application, sort of a overriding goal of the UFS is to simplify the Weather Service modeling suite. And with the RFS, we're looking to retire the NAM nests, the high-res window, and the HREF, fold that all into the RFS system at lower right. So what is the RFS? It's a 3-kilometer grid spacing modeling system over a fairly large North America region based on FE3 dynamics. It's an hourly updating system with a fairly sophisticated DA system that I really won't get into the details in the interest of time. It includes hybrid 3D and VAR with 33-kilometer members running over that North America domain. Sort of on the output side, we have deterministic forecast now going to 84 hours and ensemble forecast going to 60 hours for sort of the 4 main cycles, 0, 6, 12, and 18Z. The other cycles are deterministic, only going out to 18 hours. The deterministic system also includes smoke and dust. I'll have a slide on that. And relatively breaking news is that sort of scientific approval was given to proceed with RFSV1 by the acting NCEP director. And said I'm going to skip this in the interest of time, go on to the smoke and dust functionality. Lot of work done, I'd say primarily on the GSL side, and I look at this as kind of extending the HER smoke to the the large North America domain. So kind of have the pretty animation of vertically integrated smoke sort of advecting around the large North America domain. And with the increase in, seems like the last few summers, Canadian wildfires, it's become an increasing need for this kind of functionality. Okay, moving on to the REFS, the RFS Ensemble Forecast System. Talk a little bit about its design. So it's primarily based on FV3 dynamical core. Historically, single core cam scale ensembles have kind of struggled to produce enough spread. So we're looking to get spread, I say, wherever we can get it. The initial conditions are basically from 5 of the 30 DA ensemble members. Different members of the GAFs provide lateral boundary conditions. Have multiple physics sort of listed in the table at right, and also various forms of stochastic and other parameter perturbations also highlighted in the table. And HREF system is the inclusion of time-lagged members, in this case 6-hour-old instances of each. So on the table at right, we do include the control member as a deterministic control run as a member, plus the 5 ensemble members, and that's repeated with 6-hour-old of each. And then for Alaska and Kona, since we're not retiring the HER with RFS V1, we include the HER as an additional member for those domains. Okay, so what has changed in the RFS in the last year plus, basically since last year's UIFCW gathering? Sort of the big change was a change to use scale-aware SAS deep convection. That went in last August. And quickly thereafter, we realized we had sort of an excessive 0-hour reflectivity issue once we switched to scale-aware. Final big thing before we more or less froze the system to run our retrospectives was to tweak our damping to try to control some sort of a non-physical numerical artifact that we occasionally see in our runs. What we like to call the streaks is these little relatively high amplitude localized things streak across the domain. But we changed the damping to be stronger damping, but limited to the upper 400 hectopascals and above. And then as we say, we went into sort of the retrospective run period, had no real-time runs for about a 4-month period. And so coming out of that, within the retrospective, we did run a limited number of ensemble retros. And it was good that we did because it exposed some stability issues in one of the members. Sort of got around that by some reductions in the parameter perturbations for that member. Got that running stably. And then the other thing that led to a little bit more delay in bringing back the real-time system is that we made a pretty major overhaul of the workflow, switching to it being driven by EC-flow rather than Rakoto, sort of as a precursor to going towards operations. And as we'll see on, I believe on the next slide, we made a lake mask update just last month. Okay, so it's going to talk about some outcomes from the field evaluation, which roughly went from mid-April to the end of June this year. And pretty early on in the field evaluation, got some complaints from the Western region that the RFS lakes were too large, particularly the Great Salt Lake, but various other lakes. Asked us if we could make them more like the Her Lakes, which had sort of been tuned to their preferences. GSL definitely spearheaded the effort to update the lake mask. A lot of work and a lot of testing went into this, but it went into the real-time RFS parallel in mid-August. And at the bottom is sort of an example, sort of centered over Utah, and just showing how dramatically the Great Salt Lake is reduced by this, more reflecting of reality than whenever the data set that created the Great Salt Lake was originally developed. And another new item coming out of the field evaluation were complaints about overly moist 2-meter dew points in the western US, particularly in arid regions. And this was a nice analysis that was provided to us from some colleagues at SPC, just looking at bias over about a 1-week period. And it's basically plotted by the observed 2-meter dew point. So we have the RFS 2-meter in red, the lowest model level of the RFS in blue, and then the Her 2-meter dew point in green. We see that the RFS 2-meter dew point in red is very moist, particularly as you get down into the -6 degrees C and drier, getting into the +5 or greater moist bias, which is pretty dramatic. Even the Her, which the Western forecasters tend to like, is still overly moist at that sort of dry end of the spectrum, but certainly not as bad as the RFS 2-meter dew point. But the other thing is we see that the lowest model level in blue sort of tracks the Her much more closely than the RFS 2-meter dew point. So for some forecasting applications, just looking at the lowest model level instead of the 2-meter dew point is a reasonable workaround for them. But ultimately, we would like to solve the 2-meter diagnosed 2-meter dew point. One of the things that we'll likely do to fix the issue is to switch from a linearly diagnosed 2-meter dew point to a flux form diagnostic. And so here's just sort of a simple snapshot comparing the sort of the current RFS on the left and the possible future RFS on the right, where it's much drier, say 5 to 7 degrees C drier in sort of the arid region, sort of eastern Nevada, western Utah. Unfortunately, 2-meter fields have a feedback to the RFS soil DA, so we couldn't rush this in as a sort of a last-minute change for RFS V1. Hear more about when we do hope to get this in. Okay, so sort of a summary of some other feedback that we got from the field coming from the field evaluation. Really not going to go through these, other than I'll talk through the ones I've highlighted on this second slide here, which sort of illustrates, I think, sort of a good and bad thing from the RFS evaluation. This is coming out of the HWD period. Graphics updated by Andrew Benjamin of EMC. But anyways, looking at the observed MRMS at lower right, kind of see highlighted 2 roughly linear line segments that are what is circled. Then that same region is circled in the RFS, which doesn't capture the region perfectly, but at least seems to have more of an idea and better positioning than the other legacy cams, basically the NAM nest and the 3 high-res windows along the top. But along with the relatively good position, kind of see a somewhat exaggerated reflectivity signal, much too much coverage of sort of the 50 plus dBz, sort of the red color and the simulated reflectivity relative to observations or relative to the other cams. Okay, so getting towards the end here, just summarizing a couple of technical challenges for implementing the RFS, even though we've gotten sort of scientific approval, still need to sort of get it by NCO so they feel comfortable supporting it in operations. One aspect of the RFS is it has a huge data volume. And a lot of this data needs to be mirrored between the two sides of WCOS. Currently, the RFS ENKF restart files, the 30 members that are used in the DA, totals about 3 to 4 terabytes per cycle. Something we're looking into is compressing these with a certain amount of lossy compression. Believe we can reduce this volume by about 70% without throwing away much meaningful data, but it won't allow for bit identical restarts on the other side, assuming we need to switch systems. And then the other thing is just the CPU footprint of running 3 kilometers over a large North America domain is huge. Makes it hard to test, particularly running the full 30-member 3-kilometer DA ensemble system. Makes it hard to test, especially on other computers. Okay, so next steps for the version 1 of RFS. We're working right now on getting the system into better shape, sort of highlighted by, like on the last slide, just the compressing the data to make it more palatable for NCO to support. But other things, getting the software into better shape before handing it off. Currently hoping to do that by late October. Assuming we meet that date, current implementation target is roughly about February of next year, so hopefully at least early next calendar year. And then the thing that we're also talking about is quickly pivoting to doing a sort of a 1.1 implementation. This is where we would like to take care of the 2-meter dew point issue and also various other product requests that came in a little bit too late for V1.0. We'd like to do this about 6 months after the V1.0 implementation. So that's a challenge for us, and it's part of a new paradigm for EMC, sort of in conjunction with NCO, to strive for more frequent, more incremental updates and upgrades to be a little bit more nimble with our implementations. I think I burned through all my time, but that's it.
All right, thanks, Matt. I think we're going to move on to our next presentation. So continuing with the theme of the RFS V1 status update and evaluations from stakeholders, we have Israel Yurok from the Storm Prediction Center as one of those stakeholders that's going to give us an overview of their aspects of the evaluation of this model configuration. Israel, can you hear us?
Yes, can you hear me?
Yep, sound good. Take it away.
All right, very good. Thanks, Curtis. Yeah, so I'm going to take a look at our recent evaluation of the RFS version 1 during the 2025 NOAA HWT Spring Forecasting Experiment. This is a large effort put on by NSSL and SPC, and a lot of help from CIRO staff as well. So what is quickly the Spring Forecasting Experiment? It's a 5-week experiment where we look at real-time weather, again, organized and facilitated by SPC and NSSL, testing and evaluating the latest technologies for severe weather prediction, including CAMs. Obviously to help develop and accelerate R2O and strengthen O2R pathways. Over the past decade or longer, we've been evaluating the performance of CAMs and CAM ensembles. And then the past few years, we've really focused heavily on RFS version 1 evaluation. So Matt hit on this a little bit, but just taking back a couple years on what the RFS looked like back in 2023, our evaluation showed that RFS had systematically overly intense convection and had really an abundance of spurious storms, and that was especially noted in the 0Z initialized runs. So developers took that feedback, and to mitigate some of those aspects of the overly intense and spurious convection from 2023, they implemented convective parameterization schemes in the version for 2024, including all the ensemble members. One of the things though worth noting is that we hadn't really evaluated CAMs with deep convective parameterization schemes, so we really didn't know what to expect. So in 2024, we saw definitely tamped down the convection, the bias and POD were significantly reduced. But specifically, the Grell-Freitas scheme that was implemented overly suppressed deep convection on a number of high-impact severe weather days. So as Matt said, in 2025, the change was to go from, in the control member, from the Grell-Freitas convective scheme to the Scaleware SAS scheme. So how did that look this year? So one of the evaluations was comparing the deterministic control run to operational cams that are proposed for retirement in the Weather Service. This would be the NAM-CONUS Nest and the 3 high-res window runs, 2 ARW runs, and an FV3 run. And Matt actually showed this particular case. This is a moderate risk case from April, highlighting the RFS in the bottom middle compared to observations. This is really an excellent convective mode forecast where the convection lined out pretty quickly up there in Minnesota, Wisconsin, and more isolated, but also fairly linear convection farther south. You can see that that's handled much better in the RFS than all the other operational cams shown here. So that was, an example of where it did pretty well. So somewhat representative here of the subjective ratings on a 1 to 10 scale for these 5 different cams during the 5-week period of the SFE. These are for the 12Z runs. On the left is composite reflectivity UH. You can see the RFS had the highest median rating of 7. None of the other models had a median rating of 7 over the 5 weeks, and also the highest mean rating. So pretty good showing there compared to these particular cams. And on the right is the environmental fields, so 2-meter temperature, 2-meter dew point, and Cape fields. Again, the RFS had the highest mean ratings over all the other operational cams. So pretty good showing for RFS compared to some of those legacy cams. If we look at some of the objective statistics over these mesoscale domains of interest for severe weather, you can see in a performance diagram for 40 dBz reflectivity, the RFS, again, stands out in terms of the other operational cams it was compared against, so a good result there. And then showing the CSI by time of day. So from, again, the 12Z cycle, you can see the big advantage that the RFS has with its ensemble radar DA has a much higher CSI that lasts into the afternoon and kind of persists even through much of the convective cycle. So you can see how it has that advantage over some of these legacy cams that it's hoping to retire. We also did an evaluation of the RFS against some other what we call flagship cams. This includes the HER and some other organizations' sort of best cam that they run in real time, including NSSL impasse and GSL impasse runs. And just, I don't want to dwell on this because I think Adam will talk a little bit more about some of the GSL runs, but the RFS, where does it stand compared to some of these? It's more of the middle of the pack in terms of reflectivity, again, on the left there. The slightly below the HER and some impasse runs. Environmentally, you can look at the distributions and mean ratings. They're all pretty similar actually for the top 4 models here. So looks pretty good environmentally. It lags a little bit in terms of the structure and nature of the storm. So I'm going to talk a little bit more about that aspect specifically. So when we look at gridded performance diagram here for 40 dBz on the left, you can see the RFS, the red circle. It has different characteristics than a lot of these other cams. Definitely a little bit lower POD and a lower bias. It's just below the diagonal bias of 1. So it has a low bias, which a lot of participants had struggled with that concept because we've seen what it looks like on individual forecast hours. It looks like it has a pretty high bias. So keep in mind this is sort of grid point based frequency bias. So on the right there by forecast hour, you can see the RFS does have a low bias below 1 most of the day. It's sort of in the peak convective period, it pops above 1, but compared to the HER and the green line, for example, has quite a bit lower bias. So we were kind of scratching our heads about what that meant. It didn't really jive with our subjective impressions. But when you look at it in terms of object-based verification, I think this helps explain sort of the discrepancy here that we've seen subjectively. So on the left, we have just object counts of contiguous 40 dBz areas. The RFS, again, in the red. Notice it stands out as very low object counts compared to the other flagship cams. The observations in terms of MRMS reflectivity is the black dash line. The HER is the green line. So you can see the HER actually matches pretty closely the number of observed 40 dBz objects, where the RFS has a really low bias. But on the right, you can see that these objects are much larger than what's observed. So this is the size in terms of grid point, contiguous grid points. And you can see the RFS is a real outlier in terms of the size of the 40 dBz objects. So while gridded verification suggests it looks pretty decent, when you look at some of the attributes of the storms, they're really not all that realistic. Again, the observations here, the dashed black line, most of the models are pretty close to the observed size of storms, including the green line there. But the RFS is objects that are much larger than what's observed. And you can also see the ramp up in the early afternoon is much steeper than most of the other cams. So once you get initiation, the storms are off to the races. They grow overly large and intense too quickly in the RFS. So let's talk a little bit about the ensemble. Matt showed some of the configuration of the refs. Just want to highlight that the change from 2024 was to use the scale-aware SAS convective scheme in the control member. That's really the primary difference in the ensemble between 2024 and 2025. So we looked at the refs compared to the HREF, which is the operational cam ensemble. We looked at the 14-member, what we has labeled here as the EMC refs, and we also had an alternate configuration, what we call the SPC refs, that based on our findings, remove a lot of the time lag per term members because they generally don't perform as well as the controls, and add in time lag control members for a total of 10 members in that configuration. So when we look at a couple examples, this is the HREFs in the left column, the EMC refs in the middle, and SPC refs on the right. The top row is the 0Z run for April 29th. The bottom row is the 12Z run. In this particular day, was enhanced risk, and there was an ongoing severe MCS, you can see, with a lot of severe and tornado warnings. Early in the sort of midday period, this is valid 17Z. So it's a 17-hour forecast on top and 5-hour forecast on the bottom. And I don't know if you can see the details in the room there, but you have 70 and 90% areas in the bottom middle and bottom right panels. Because you're simulating the storms there, you have a much higher probability appropriately in the refs configurations compared to the HREF, which a lot of the members are still cold start, and so you only have a 30% probability there. So we see big advantages in the radar DA here in the refs. In another case, an enhanced risk in May up in the Midwest. The top row again is 0Z, bottom row is 12Z. Again, subjectively, these ensembles are pretty similar. So I had to look pretty hard to find a case where the ensembles had apparent differences. In this particular case, I'm highlighting northern Indiana and northwestern Ohio, where the HREF had higher probabilities where nothing happened, and the refs in the bottom middle, bottom right, when you're looking at 12Z runs here, were more appropriately shifted a little bit north, had a little bit better axis of probabilities where severe weather occurred. Generally pretty similar, but again, this is a case where the refs had a clear subjective rating advantage. So when we look at those rating advantages, here we have both the 0 and 12Z runs rated together. We have the 3 different ensembles. On the left for composite reflectivity, on the right for updraft helicity. What we saw overall in the experiment is that the 12Z run, the most recent run of the SPC refs configurations, had a very slight edge over the EMC refs configuration, and then followed generally by the HREF. So this is really the first time where we had a cam ensemble that subjectively was rated higher than HREF, so it's a pretty big deal here during the spring forecasting experiment. When we look at some of the objective verification, it does sort of agree with those subjective ratings. This is for 40 dBz reflectivity. This is the HREF are the stars, SPC refs is the boxes, and the circles are the EMC refs. You can see that the boxes and circles, especially as you get to the blue, the 40%, the browns 50%, and so on, you see they lie on the similar performance curve, where the HREF starts to lag, has a little bit higher false alarm, so it lies to the left of those. And of those SPC refs I've highlighted here in this red oval, tended to perform more similarly to the HREF. So it had a similar POD, but a lower false alarm. So generally had a little bit higher CSI in the SPC refs configuration. So it's a pretty good objective finding as well. And then I won't dwell on this, but the statistical reliability of these systems are all pretty good, which is a nice result as well, without any additional calibration. So here, just to sort of wrap up, the RFS deterministic performed favorably over the 5 weeks of the SFE compared to operational cams, especially NAM Nest and high-res window runs. Maybe still lagging behind the HER, but again, the HER's not going to be retired yet, so that's a good thing. We did hear continued comments and concerns about the character and realism of the storms. Storms are definitely too intense and too large in weak shear environments. It's not as big of a deal often when you have stronger shear. But overall, the placement timing convective motor generally pretty reasonable and usable in operations. In terms of the ensemble, the refs ensemble and HREF were surprisingly similar when you look at neighborhood probability fields for reflectivity and UH on most days. There is less spread in the refs, which often results in higher probabilities, but they're often more accurate spatially. So you have sort of a refined higher probabilities of where activity actually occurs. And just a quick note at the end here, just that we did see run-to-run, week-to-week variability in the performance. So definitely any generalizations, you have to look at multiple weeks of data to try to generalize any findings. So with that, I'm happy to take questions if there's time.
We do have time for a question or so. If anybody wants to chime in, come up to the microphone here, please, if you're got a question. Not. Okay. We'll keep moving then. Oh, do we have one online? Oh, go for it.
No, I just had a question.
Yeah.
So were there any, and obviously this is not going to be generalizable to model performance, but were there any specific events this spring that the RFS had really standout performance on?
Nothing comes to mind. The May 15th event that I showed there was one where it did pretty well, but I wouldn't say there was any standout. I think more importantly, there wasn't any standout bad performances, I think is probably the safer comment that I can make.
All right, thanks again, Israel.
Yep.
All right, so we're going to switch gears a little bit and talk a little bit more forward-looking beyond RFS version 1.0 and discuss MPAS being brought into the UFS weather model from GSL and DTC's work, and Dustin Swales will take it over.
Thanks, Curtis. All right, so a little bit of a different feel to this. In the first two talks, we'll be talking more about the engineering and infrastructure of the UFS model and how MPAS is going to fit into that. There's a lot of considerations about the scientific different approaches of the different dynamical cores that we have to account for when we're doing this building of the infrastructure. So I'd like to thank all my collaborators here. I won't go through the names, but the usual who's who of people doing good stuff. Okay, so I guess the first thing is just to put some goals and questions out there and kind of frame this a little bit better, because when you say putting MPAS in the UFS, that can mean a lot of different things. It can mean the whole thing, or it can mean a little bit, or I guess I'll try to talk through that right now. So our initial target is for Rufus V2 applications, for short-range weather application forecasts. So that is our main goal. So one caveat I should mention about that is these Rufus forecasts are regional, and they're uncoupled simulations. So in a sense, it doesn't rely on as much infrastructure as, say, a global coupled simulation to implement the MPAS dynamical core for. So one of the main goals is to generalize the infrastructure of the existing UFS, which is an FV3-based dynamical core model, to be able to use multiple dynamical cores where you could choose your dynamical core based on your application and couple to the same physics that's shared across applications. So one big question is, how much of this infrastructure could we share? How much of this can we leverage and generalize and make model agnostic so that we could share it across the dynamical cores? And then after that, the following question is, what do we need to build? So what can we use, what can we build from the FV3 to use in MPAS are kind of the main overarching questions we're going to talk about. So some real basic background here to kind of give people a little bit more of a bearing. So the UFS is a multi-component or system model, ocean, atmosphere, et cetera, whereas MPAS is a standalone atmosphere model that has its own physics and its own dynamics. There is coupling within MPAS that I won't talk about, but that's outside of the scope of this. So one thing we are trying to do is, can we use the MPAS dynamical core within the UFS and still use the same physics in the UFS that we've developed for Rufus V1, and then just switch die cores and move on to Rufus V2. So that's kind of what we want to ultimately do in the UFS. So one way to do this is by, generalizing the code base so that you could switch your dynamical cores for different applications. So there's a couple caveats to this here. Within the atmosphere model, there's generally two pieces, the physics and the dynamics, and how they're coupled together is very important for how the forecast gets integrated forward. And in this context, we have for the UFS, the FE3 and the CCPP. And for MPAS, they have their own physics, which are connected loosely to the CCPP physics through submodules. Clark Evans will probably talk about that in the next talk, about how we are managing this physics development that's going on right now between the standalone MPAS and the future MPAS in the UFS, or inline MPAS. And not to minimize any other parts of the atmosphere component, like there are other pieces within the atmosphere that are really important. Like for example, UPP we need to use for production capabilities, but it's not really fundamental at first to get the physics and dynamics hooked up. And additionally, stochastic physics is part of the atmosphere, but I'll talk about that a little bit later. So here is an overview of the architecture of the UFS at the moment. So from left to right is the highermost level of the model, so the UFS model. And as you go down, we're getting into different components of the model. So the first column to the right of the UFS weather model are the Earth system model components. So this is a very simplified schematic of the architecture. I'm just focusing on the atmosphere right here, but I put MOM6 in there in an empty box just to show how the ESMF infrastructure, which is denoted with these orange arrows, connects the different components together within the UFS. And then if you go down a layer further, you are in the actual atmospheric component where you have the physics and the dynamical core, and those are coupled together. And if you go even all the way to the right, if you look in the physics, there's different subcomponents of the physics, so different parameterizations that may come in as their own components or submodules in this case. So there's a couple different places that I want to focus on here, and the colors of the arrows are kind of indicative of the infrastructure involved. So in this part of the coupling right here, I have highlighted in blue and circled as kind of this intra-atmosphere coupling between the physics components. So this could be between radiation and microphysics and all the different groups. That's where the CCPP comes into play. The CCPP is the infrastructure for the physics. It connects all these different schemes and groups together into either different groups or an API that is called by the host model. It doesn't have anything to do with the dynamics. Some people always conflate the CCPP with the dynamics coupling, but it's really distinct, and it's just the groups of physics and the physics suite in itself that is in charge of coupling. So if you go up another layer, the actual piece where the physics dynamics coupling occurs is in the atmospheric driver. So this is not reliant on any particular infrastructure. It's traditional coding that grabs the pieces of the CCPP physics and it calls the die core and it puts all that stuff together. So this is where the actual forecast happens and it integrates forward. So for that, no infrastructure, just traditional programming techniques. And then if you go up another layer, we have the ESMF. So this is basically the component coupling of the Earth system model. So these are the three distinct points of modifications we need to make to the UFS to implement a new dynamical core. But the most important piece, I want to kind of highlight is this. This is where all of the real work is this physics dynamics coupling that happens in the atmospheric driver. The changes that we need to make to the model in terms of like ESMF and new OPSI are not as great as the changes we need to make in here to couple the physics to the dynamics. Similarly, the changes we need to make in the physics aren't that great either. There's some cleanup and generalization we need to do, but this is really where the work is, in this piece right here. And everything from here that we need to do kind of permeates either up into the ESMF and new OPSI components or permeates down into the physics and the die core itself. So this is kind of like the central piece, the physics dynamics coupling. So I'm going to start there rather than start at the top or at the bottom. So on the left-hand side, we have a schematic of how the forecast integrates forward for an FE3 CCPP-based atmosphere, where we call the dynamics, we call the physics, we combine those states together, we call the coupling infrastructure, and then we kind of go around in a circle. And that's how we do things in the FE3 world. There's some subtleties to what are in the physics and how the state is handled in between the physics and the die core, but that's not really terribly important for this point for the FE3. On the other side, we have what happens in the MPAS. So the MPAS does a quite different forward integration process where it calls all of its physics initially first, then it calls the dynamics, and then it calls the microphysics. And in between them, there's some different manipulations of the state variables, and tendencies are applied in different places so that it could provide all the necessary coupling to the MPAS model. So most specifically is in MPAS, we have to call the dynamics and then remove the heating tendency from the previous time step and then call the microphysics. So there's these kind of coupling steps that we need to build into the physics dynamics coupling for this to really work. Because we don't do that with FE3. We do different things in FE3. For example, we have a fast physics section that calls the saturation adjustment from the dynamical core in certain microphysical schemes. So there's actually a tighter coupling to the dynamics there. So there's different pieces of the modeling system that get, that need to be modified for the MPAS with respect to FE3. Going down a level, so into the physics, MPAS and FE3 handle the physics very differently, just like any host model handles the internal physics state differently. I don't know what the rhyme or reason behind why modeling centers chose how to evolve the state of their models, but they all do it in a different way. If you look at CESM, or if you look at MPAS and you look at the UFS, they're all doing different types of process splitting and time splitting, which basically means, do you call a scheme and update the state, or do you call a bunch of schemes together and update the state later? So for MPAS, they call all of the schemes at once using the same state and then update the state. So they do a pure process splitting section before calling the dynamics. And then after the dynamics, they call the microphysics, which actually updates the state. So it's like a time splitting section. But because it's only one scheme, there's really no difference between the definitions at that point. So these schematics here kind of highlight the difference between these two types of processing. So on the top row, we have purely process splitting, where all the schemes see the same input state, we update the state, and we march on in the evolution. Whereas on the bottom, each scheme sees a state, sees a different state, updates the physics state, and then marches on. So these are different philosophies that are very different across different host models. And this is kind of one of those coupling things that we need to generalize so that we can call physics either in process split or in time split, because if we're using an MPAS die-core versus an FE3 die-core, we need to process split the physics differently than if we were doing it in the FE3. So generalizing the physics to be able to do this with any physics schemes was part of our initial effort of work to get ready for MPAS. So another type of coupling thing is three-dimensional physics. So this one is stochastic physics. So for here, this is how we did it in FE3. This is that same schematic of how the state evolves within the atmosphere, where we call the physics and the dynamics. But now I've inserted calls to where the stochastic processes get invoked. So there's additional parts of the forward integration to call a pattern generator that you need the dynamics for, and then you produce these perturbations that you either pass to the physics or you use the stochastic physics. And anyway, so this is just kind of how the state evolves differently when you're coupling in a three-dimensional sense. This is kind of the same thing if you were doing 3D physics coupling. So say if you needed to compute gradients of fields, you would kind of do it at this level and then pass it into the physics from the dynamics. So that's where the three-dimensionality comes, using the halo or the surrounding points to derive quantities that you could use at the grid mean and pass in. So that's kind of where the 3D physics part comes in. So there's efforts underway to do this in standalone MPAS at the moment, and there's plans to then transfer what is done in standalone MPAS to UFS MPAS when the time comes. So the last piece of infrastructure is the piece on the top. This is ESMF and new OPSI stuff that we've heard a lot about this week. But this is basically the part that, there's a couple different parts, I should back up. The forecast grid component is the part that actually integrates the model forward in time. Then there's a write grid component that actually does asynchronous I/O. So in operations, it's very important to continue running the model while you're still outputting from before so that you can make products in a timely fashion. So the write grid component provides asynchronous output and I/O to speed this up. MPAS has native PIO that we're using at the time being, but ultimately for operational runs, we're going to need to have a forecast write grid component so that we could output stuff quickly. And in addition to the ESMF infrastructure, there's the new OPSI cap. So this enables either FE3 or MPAS forecasts to integrate forward in time and couple to the other Earth system model components. So for Rufus, we didn't have to talk about any of the other coupling, but for other particular applications, you will need to couple to other components. And that would happen in this new OPSI layer. So I guess now is the status update of where things stand. So we have refactored the UFS code. This just got in about a week and a half ago. So the FE3 atmosphere is now the UFS ATM. So it's been completely generalized into FE3 and MPAS specific parts. The physics have been isolated to sit at the same level as the dynamics so that we can couple the same physics to the dynamics. Also, the physics have been refactored to all produce physical tendencies coming out of them. So we've totally removed the functionality of schemes to modify the state directly. All that schemes could do is take a state and report a tendency. And it's up to the host, whether that's an FE3-based host in UFS or an MPAS-based host, to then use those states accordingly based on the dynamics and physics coupling paradigm that you're following. So that was part of the generalization. And as I mentioned, the stochastic physics is under development and standalone, and that will eventually get moved into the inline UFS at some point. And we have this initial NUOPSI ESMF infrastructure in place to actually call UFS forecast with the MPAS model now. There's a regression test in there for us to do it. It doesn't do anything, it just calls the initialization and goes away. But our next step is to build out this physics and dynamics coupling so that you can integrate forward with MPAS forecasts. So this is kind of a snapshot of where the architecture stands now. The only difference between this picture and the previous one is there's an MPAS model in there now. And the green arrow has been, added there to start the coupling between the CCPP physics and the MPAS dicore. And I should also mention we have a generalized NUOPSI cap for the atmospheric component. We don't have individual NUOPSI caps for the different dicore physics. We have one NUOPSI cap, but then we have different forecast grid components that combine in that NUOPSI cap, whether it's an MPAS or an FE3 forecast. Perfect. Okay, so the next steps for Rufus, we need, like I mentioned, we need to build this physics dynamics coupling out so we can actually integrate forward, taking into account all that stuff I mentioned before about the specific state evolution that we need to do. Then we need to do the integrate of the stochastic physics, which is underway. So after all the dynamics and physics are hooked up, we'll move on to that. And also this ESMF right grid component so we could have production capabilities. And then beyond Rufus, there's questions on how, where we go with this. For global applications, we need more work to couple to the other components. You may want to think about how we want to do this before we actually do it, because, for example, like HAFS has this whole moving nested grid thing. That is something that could be entirely maybe redone with MPAS and the way it handled its mesh. So there may be more opportunities going forward to use MPAS for different applications in different ways than we've used. And also, this will enable a lot of science questions about how to study physics and dynamics coupling. Because we'll be using the same physics and dynamics, and we have strict control over the coupling, one could easily make up some pretty cool test cases to see how sensitive, forecasts are to different evolutions of the prognostic state. Done.
Yeah, I think we're going to move on for the sake of time. So thank you again, Dustin. Our next presenter, we're going to have Clark Evans speaking to more of the development activities in GSL with MPAS as we move beyond, like I said, RFS version 1.0.
All right, thank you, Curtis. And apologies to, I think, Adam, who follows me as I lift up the project this thing, or at least try to lift it up to be a little bit higher for my insanely large height. I think, there we go. All right, so this is really a big effort across GSL. There's only a limited number of people listed here on the title slide. I could list 50 more easily. And this has benefited from discussions across NOAA with our partners in the Weather Service, EMC, stakeholders at the national centers, and even down to the WFOs. So you'll note a slight change of my title from what is in the agenda. The agenda says Rufus version 2. There's a purposeful takeout of that here as plans continue to evolve for what an implementation of an MPAS-based forecast system in NOAA operations could look like. So this talk's going to focus more generally on our work with MPAS for next generation, nominally regional forecast system development. All right, so the bulk of our work here at GSL over the last year and a half or so has been utilizing MPAS, a model for prediction across scales. Our colleagues on the data assimilation side have been working to extend out the functionality of JEDI, a joint effort for data assimilation integration, to build out a long-term vision for a coordinated MPAS plus JEDI Rufus version 2, or whatever we may wish to call it, forecast system. Our cold start forecasts utilizing MPAS have been evaluated in multiple NOAA testbeds. See two examples here on the right. with the hazardous weather testbed spring forecast experiment at upper left and the winter weather experiment here at lower left. We've been running real-time regional all the way down to 1 kilometer and global all the way up to uniform resolution 15 kilometer and variable resolution 15 to 3 kilometer global forecasts. This work has really helped us advance our physics parameterizations, and I'll discuss a little bit more about the testing and evaluation strategy momentarily. And this includes purpose-built forecast systems, such as we have in the upper right here with the forecast of Hurricane Milton during last year's Hurricane Forecast Improvement Project, where we were able to explicitly represent eyewall replacement cycle at 2 to 3 day lead time in close coordination with observations. So at GSL, we have 3 regional MPAS-based prototypes or development systems toward a next-generation rapid refresh forecast system. All of these are using the community. NCAR refers to it more as the community. In NOAA, we've referred to it more as the standalone community or standalone MPAS version 8.3 code that was released earlier this summer, as well as physics advances developed at GSL. And the next slide will go into more detail about that. Our baseline is what we call MPAS Rufus A. This utilizes the Rufus A, now the pre-operational Rufus version 1 prototype, for its initial lateral boundary and aerosol initialization conditions over a CONUS domain. We run that 8 times per day, right now 4 times out to 84 hours, and the other 4 times out to 24 hours. We have plans to extend this out to a larger domain beyond just the CONUS to begin preparing for potential operational implementations. We have 2 physics and dynamics testing systems, what we call Dev1 and Dev2, slightly different run times and run frequencies relative to each other. But apart from that, these differ from the baseline with only single physics or dynamics changes. Like for instance, right now we've been running a test of our microphysics parameterization in one and a test of Smagorinsky mixing in the other. We've had an extensive effort in the middle portion of last year to integrate the GSL-led physics suite that we've seen from HER v1 through v4 and into Rufus version 1 over into the standalone or the community MPAS implementation. So all of these exist now within the GSL or UFS community version of the MPAS version 8.3 code, although we are using the NSF NCAR version of the RRTMG radiation parameterizations. I'm not going to go into detail about all of the changes that are listed here. That notes column details relative status for each of these parameterizations. I do want to point out something that Matt brought up with the diagnostics for 2-meter fields in Rufus version 1. We have reverted that in the RUC LSM back to what was seen with HER with the flux form of the diagnostics, and that'll influence the results that I'll show in just a few moments. MYNN EDMF has recently been updated to be now a level 2.7 closure scheme with total turbulent energy. We are not using a deep cumulus parameterization. We ran several months of parallel tests with and without last year at 3 kilometers over the CONUS and found no impact to the forecasts that warranted continuing to use that. So that's a big change from Rufus version 1. We also have updated from the Thomson-Eidhammer to the new Thomson-Eidhammer microphysics parameterization for operations, or TEMPO, that includes a machine learning diagnostic for number concentrations to give life to the PBL clouds, as well as new freezing rain and hail diagnostics. The Unified Gravity Wave Physics package is available in NSF NCAR's, or the community version of MPAS, and we have plans to bring MYNN EDMF and TEMPO there with the PRs likely toward the end of this month, potentially slightly later. So the next few slides are going to talk a little bit about performance. Like, I'm not going to rehash the strengths and the weaknesses of Rufus version 1 necessarily, but we've been running these forecasts for over a year now in real time with a relatively consistent forecast system over the last 4 months, evaluated in multiple NOAA test beds. I'm going to step through some of the performance characteristics, upper air, surface, and single layer fields here. So the next series of charts, HER v4 will always be in red, Rufus A or Rufus version 1 will always be in blue, and our MPAS Rufus A forecasts in the yellow or the gold here. Our MSC will be solid, and bias will be dashed lines, a 4-month period from mid-April through mid-August. Upper air fields will be 12-hour forecasts. And at each point along the graphs, the bars represent the 95% confidence interval. One of the most notable changes here is that the MPAS Rufus A forecasts have significantly improved RMSE for temperature throughout the lower to middle troposphere, and significantly improved and in fact near zero biases throughout much of the troposphere, as compared to HER, which was cool biased, and Rufus version 1, which is slightly warm biased. If we go to relative humidity, here relative to radiosondes, there's an important caveat for that I'll get into in a moment here. Not quite as good of performance. We're slightly higher RMSE in the mid-troposphere with slightly drier bias, but competitive in the lower to upper troposphere. Note that these are relative to radiosondes. Work elsewhere within GSL has demonstrated that the radiosondes are insufficiently responsive in cloud and moist layers, so we have reason to believe that these are generous in terms of their representation of a dry bias. The truth is likely even more shifted to the left on these bias curves. If we take a look at wind speed, very similar across the three models over this 4-month evaluation period. Moving down to the surface, the x-axis now becomes the forecast hour, 0 to 24 hours here. Looking again at HER, Rufus, and MPAS Rufus A. Note the difference in the diagnostics. So the better comparison, I think, here is HER versus MPAS Rufus A as opposed to Rufus A or Rufus version 1 against MPAS Rufus A, because they use a consistent form of the diagnostic method between them. Here we see that beyond 3 to 6 hours in the forecast, the HER and MPAS Rufus A have nearly identical RMSE characteristics, with a significant reduction in the warm bias associated with the HER forecasts between forecast hours 6 and 18 here. If we look at 2-meter dew point, you'd look at this initially and say, wow, Rufus version 1 is great. But as Matt's presentation went into some detail earlier, this is kind of masking the overall dryness that should be there within the western United States. But compared to HER-V4, a significant improvement in both the RMSE, reduction of 1 to 2/10 of a degree Celsius, and improvement in the bias characteristics by about the same 1 to 2/10 of a degree Celsius. We take a look at wind speed, again, slightly improved in MPAS Rufus A as compared to both HER-V4 and Rufus version 1 for both RMSE and bias out to 24 hours. Take a look at downwelling shortwave radiation verification here. There is some weirdness in the Rufus version 1 evaluation in that it seems to have about a 30-minute time lag in the radiation that manifests in this, let's see here, this negative bias early in the day and this significant positive bias later in the day, whereas HER-V4 and MPAS Rufus A don't have that. The RMSE between those two are very similar to each other, but the MPAS Rufus A bias is significantly reduced as compared to HER-V4 throughout the daytime hours. Looking at composite reflectivity verification, we only have this for HER versus MPAS Rufus A. Now looking at CSI at 20 dBz on the top, 35 dBz in the middle, and 45 dBz here on the bottom, with hour of day now as the x-axis. HER with data assimilation and MPAS Rufus A without it are nearly identical in these 12-hour forecasts at all of these times apart from the overnight. We see some limitations in our forecasts. They tend to dissipate organized convective systems a little too early during the evening hours and have some struggles with depicting elevated convection initiation during the overnight. But throughout the peak convective period during the daytime hours through this warm season, very similar performance at all three of these thresholds. And then precipitation, here we're looking at a performance diagram, and I've labeled the specific thresholds there on the chart. Slightly better performance at the lowest threshold, 0.01. Slightly degraded in the middle thresholds, but then for the higher thresholds, 1, 1.5, 2, and 3 inches, nearly identical CSI with a slightly reduced bias, near 1 bias for each of those thresholds, and MPAS Rufus A as compared to HER-V4. So I think we have a forecast system with MPAS initialized off of the Rufus version 1 data that is at least comparable, if not in several ways superior to what we are seeing with HER-V4, which has been in operations for nearly 5 years, and the prototype RRFS version 1. One of the big issues with Rufus version 1 has been its representation of deep moist convection. Here I'm showing an example from the spring forecast experiment. This was a slow-moving upper low in the southeastern and mid-Atlantic United States, where there was isolated but mostly disorganized deep moist convection initiating over the southern Appalachians throughout the afternoon hours. The environmental fields here on the left are very similar between RFS version 1 and our MPAS forecast initialized off of the same data, 19 hours into the forecast. But the composite reflectivity fields are very different. The intense convective cores with RFS here on the top, we do not see that behavior with the MPAS-based forecasts here at the bottom. And this is consistent across the entire spring experiment and all of our real-time tests that we've run over the course of the past year or so. A substantially improved depiction of convective systems, here showing isolated convection. And one of the things the spring forecast experiment really helped highlight, organized mesoscale convective systems. The stratiform precipitation regions look more realistic in our MPAS forecasts as compared to those from other numerical models. And I think Adam will go into a little bit of detail with an example of that in his talk. As mentioned, we've had a number of testbed evaluations. Spring forecast experiment was the big one this spring. I think Matt had a version of this slide, or Israel, and I think Adam has a version of this image here as well. We've also been evaluated in the winter weather experiment late last year and earlier this year that really helped us to diagnose some issues with our forecasts in winter weather conditions. Precipitation experiment for atmospheric rivers, a limited set of 2 cases, but here in this example, better forecasts are on the left-hand side of the diagram, and for both of those cases that we provided forecasts, the MPAS forecasts were rated best by all of the participants. These testbed evaluations are a great example of partnership from OAR to the National Weather Service, helping us create better models for a wide range of stakeholders and a wide range of meteorological conditions. Let's see. Ming talked a little bit in his presentation yesterday about our work with regards to JEDI, so I'm not going to go into great detail here, but I do want to point out the real-time systems that our data assimilation colleagues have been running, particularly this Dev3 with cycling and reproducibility tests. That has helped us identify issues with our physics not completely being bitwise reproducible in cycling tests that we've been actively working with our DA colleagues to address so that they have the right state to be able to work from moving forward, in addition to the natural interplay between DA and physics that takes place within the forecast system as a whole. We also have a number of other MPAS-based applications taking place here at GSL. Full system with aerosols, including smoke, dust, pollen, and more. We're about to begin testing in our real-time systems of a smoke and dust implementation, similar to that seen within Rufus version 1. We're excited to get that started, hopefully within the next 1 to 2 weeks. We also run really high resolution forecasts, 1 kilometer over the western US with rave emissions for fire weather, and 1.25 kilometer over the eastern 2/3 of the United States. We've done tropical cyclone forecasts as part of the Hurricane Forecast Improvement Program, and I mentioned briefly our global forecasts as well, including what we're running for the Hurricane Forecast Improvement Program, variable resolution global, with 3 kilometers over the entire Atlantic Basin. Dustin just talked about this, the integration of the MPAS dynamical core into the UFS with this same graphic. So I'm not going to go into a lot of detail here, but this is a key thrust of GSL development efforts over the course of the next 1 to 3 years. So where do we go from here? It's a top priority that to improve RFS to transition to MPAS. What exactly that looks like is still being discussed and determined. So I'm not really feeling comfortable in being in a position to express publicly exactly what that looks like, but hopefully soon. GSL work continues on many, many fronts with physics, stochastic physics, data assimilation, integration in the UFS, scoping of dynamics, numerics, and filtering options in collaboration with NSSL and others, and potential integration into the workflow of unified workflow tools. Plus, we're also beginning to scope out the GPU capabilities available within the community MPAS. So with that, I'm at time. Thank you for your attention.
Again, I think for the sake of time, we're going to move on. So we're going to pivot somewhat mirroring the V1 with this work beyond V1 to how these prototype configurations with MPAS performed in the spring forecast experiment testbed evaluations. And for that, we have Adam Clark from NSSL.
Clark, you didn't make me tall enough, I feel like. There. I won't worry about it. All righty. So I just want to thank the co-authors first, and then thank all the people that contributed to making our 2025 SFE a success. So our spring forecasting experiments are 5 weeks long. We hold them at the peak of this severe weather season, typically most of the month of May. They are jointly organized and ran by the Storm Prediction Center and the National Severe Storms Laboratory. Our 25 SFE was hybrid. It's the third year in a row that we've had a hybrid experiment. 75 people were remote and 56 were in person. That ratio was reversed the previous year, so now we have more remote just because of all the government travel restrictions. Hopefully we can go back to that previous ratio next year. Our goals include testing and evaluating emerging technologies for severe weather prediction. Of course, we want to accelerate R2O, develop and strengthen these O2R pathways, and relevant to this talk, we really want to inform UFS system development, so optimize both deterministic and ensemble CAM configurations. And we do this with a thing that we call the community leveraged unified ensemble framework. Really, this is just a way for us to coordinate between all of our contributors and do controlled comparisons. So the MPAS work that we did in this year's experiment, we had contributions from NSSL, GSL, and NCAR. MPAS is replacing WRF in our Warn on Forecast system, and also FV3 and Rufus V2. This is the third year that we've done these evaluations, and it's been really kind of exhilarating to see the progress that is getting made, building on each subsequent year. So to put our results into context, I like to show what the severe weather activity looked like for 2025. And so this is just showing these cumulative LSR counts for tornadoes, wind, and hail. And so we had this several big periods of severe weather in March and April, but May was pretty normal. There were some pretty active periods and some pretty down periods, but you can kind of see, if you look at that red line, it parallels the CLIMO line through most of May, and that's the SFE period I have highlighted by that box. The previous year was one of the most active years that we've ever had in the SFE, so this is going a little bit back to normal. All right. So this is a table. It shows all of the model contributions that we examined in the SFE. The ones highlighted in yellow are ones that used MPAS. And so NSSL had 3 unique regional configurations initialized at 0 and 12Z. 2 were initialized from HER, and they had Thompson and NSSL microphysics. That was the only difference between them. And then another pair of runs where one was initialized from RRFS with Thompson microphysics. So we had kind of an initial condition comparison that we could do and a microphysics comparison that we can do. From GSL, we had our what we called the Rufus V2 development system, and then they also ran a identical configuration, except the grid spacing was a little bit more coarse with 3.5 kilometer grid spacing. So we did daily evaluations of that. And then NCAR contributed an 8-member ensemble, and they also had a global 3-kilometer CAM that they ran. That was kind of interesting. And so the ensemble, it was GEFS initialized and had the refined mesh over the CONUS. NCAR MPAS GBL or global had that global 3-kilometer mesh initialized from GFS. And then there was a control for that that was run over the globe with a coarser mesh, and then the refined mesh over the CONUS, configured similarly to that global run. So this is just showing a couple of the websites where you can look at the visualizations for those forecasts, so ensemble.ucar.edu. And then I guess I'll advertise, I guess NCAR, I just saw this, they're running global 5-day runs with a 3.5 kilometer grid spacing mesh. And I think they just started doing this. So check it out. I think you can get to those forecasts from ensemble.ucar.edu. And then the NSSL website is that CAMS one below it. And we run those year round. And in fact, we just updated our configuration. So you can go to those and look at the daily forecasts. So this is just a table showing all of the evaluations that we did this year. The ones that I've highlighted are the ones that involved MPAS. So these are just one component of what we do in the SFE. Our major themes this year, Israel talked about this earlier, the Rufus and REFS evaluations, and then we have our MPAS development. We did evaluations of the global AI emulators, and also we looked at medium range hazard forecasts. All right, so first evaluation focused on MPAS is this day one 0Z deterministic flagships. So this is where we're just looking at a deterministic model contributed by each agency and then gauging the progress for severe weather predictions relative to the HER. So there's a different model in each panel. We looked at RRFS, NASA GEOS, so this is an FV3 configuration contributed by NASA. MPAS RT is from NSSL, GSL MPAS, HER, and then the MRMS observations are on the bottom right. So this is just a snapshot. We looked at an animation covering hours 12 to 36. When we do these comparisons and when we assign the subjective ratings, you cannot see the model labels. So they are blinded. You don't know which model you're looking at. So, we don't want to introduce any biases. So just to show some of the types of errors that we're looking for when we're assigning these subjective ratings, you can kind of see this area of interest circled. If you look at GSL MPAS there in the bottom left, there were some displacement errors. Overall, the area of storms was well forecast, just a little bit off. There were supercells in southern Kentucky that I kind of have indicated there that were predicted well. In the HER, in the bottom middle, you had two areas of spurious convection, although the main line of convection was probably better placed. The supercells in southern Kentucky ahead of that line were missed, though. And so yeah, we're doing this every single day, looking at many snapshots that that we're animating, and then we have many forecasters that are submitting their ratings. All right, and so what we get out of that, these violin plots, which we now I'm showing for the third time, I guess, but the key result from this year was that the models that we looked at, the ratings were tightly clustered, so there were not big differences between the top performing models, but the GSL MPAS one did come out on top, followed by the HER. So the differences in the previous years, there was a lot more spread in these ratings. So I guess it's good to see that we're clustering together and getting overall good performance. So that's what I just said. The new thing that we did this year was we looked at weekly results. So we had on Friday afternoons a period of time when we would just go back and look at all of the compilations of results from that week, which was kind of a cool thing to do that we haven't done in the past. And what we learned is that it is really important to, because we got such variable results, so you really have to look at multiple weeks to get a full picture of the forecast skill. So just to illustrate that, here are those same violin plots, but week by week, so all 5 weeks of the experiment. If you look at weeks 1 and 2, you have a mirror image. So the top performing model on week 1, which was the HER, was the worst performing model in week 2, and vice versa. So NASA GEOS was the worst in week 1, it was the best in week 2. But one key thing I'll point out is in week 3, that was probably our most active severe weather week. GSL MPAS really stood out as having the best performance that week for the highest impact event. So I think that's really important to note there. All right, so here's a performance diagram. We also generate these. This is for simulated reflectivity. We do some neighborhooding to account for some of the spatial location errors. This is really interesting because the subjective results, where the GSL MPAS performed the best, did not match what we saw in these objective metrics. So we hypothesized that maybe the lower bias, which is actually more realistic, closer to 1, in GSL MPAS, was having an impact on these verification metrics, which are very easy to game if you know what you're doing. And just as an example, this is an MCS. The MRMS obs are on the bottom left. GSL MPAS is in the upper left. If you look at the character of the convective cells and then the stratiform region GSL MPAS really nails it. It's got the right structure, the right intensity, location. The Nissl MPAS on the upper right and then the bottom right, which is the HER, you don't really even see stratiform regions or the trailing stratiform, and then you see that high bias in the reflectivity. But those two models in the objective metrics performed better than GSL MPAS, which this is just one case. But this is why we look at these instead of just going by the statistics. You really have to spend time and look at them in this way to learn about them and get insight. So this is the same type of thing, but instead of the UH and the reflectivity, it's for the environment fields, really tightly clustered performance. In fact, the top 3 models were rated identically here. So in order, you have Nissl MPAS, HER, and then GSL MPAS. Okay, so I wanted to say a couple things about some of the other evaluations that we did. So when we compared the 3 kilometer and the 3.5 kilometer grid spacing runs, it was almost impossible to distinguish them. And so I really do think that with MPAS, which has a higher effective resolution than some other convection allowing models, we can get away with running slightly coarser grids than 3 kilometer to save computational expense. And then the plot down there is just showing an example. The 3 kilometer in the left, 3.5 in the middle. If you blurred out the grid spacing there, I'm not sure you could tell which was which. And then we also did these comparisons between the global and then the global with refined mesh. We did this at day 2. You really need to look at longer lead times for the differences to manifest and to get the benefits from running a global cam where some of the teleconnections are actually going to start having an impact. But we did it anyway just because it was a cool demonstration, and like we expected, we didn't see much difference. And then finally, we did this cool experiment where we're inputting predictors at day 5 from a cam ensemble and then from the GEFs to generate these SPC-style severe weather forecasts. And so we hypothesized that maybe at extended lead times, we could get a better severe weather forecast by having predictors like updraft helicity, the storm attributes that you don't have in coarser models. And it turned out that in some cases the cam helped. Like at the bottom row, the convection that was severe in northeast Colorado was better depicted. But then in the top row, the corridor of severe weather reports wasn't forecast as well with the CAM data. And then overall, the distributions of the subjective ratings ended up being pretty similar between these two. So we want to keep doing these types of experiments in the extended range to see if using CAM data helps. And that is it. I'll end it on this slide. Our final report just came out. If you scan that QR code there on the right, you can access it. And that's it. Thank you.
Okay, we do have time for a question or two if anybody wants to step up to the mic. Nope. I think we're going to have a question for you.
I don't know how much you would know about this because it's more on the computing side. I imagine there's significant storage and computational challenges with running a 3-kilometer global grid. Can you speak to that at all?
Yes. Yeah, I don't know. I would be curious to know how much data a single global 3-kilometer run takes up, but I can't answer that. The NCAR folks that did those would probably be better to ask them. I don't know if any of them are here and can speak up on that. Sure.
Tried at GSL to do global 3 or global 4 kilometer with MPAS, and the initialization file alone is over a terabyte. The output files are large as well. You can tweak things, and I know they've done a lot of work at NCAR to cut down on the output to save disk space, but it's very, very expensive.
All right, thank you again, Adam. All right, so our last presenter from DTC, Michelle Harold's going to speak to how we can continue to improve our abilities to verify a lot of these model configurations to assess their performance objectively with Met Plus. So we'll turn it over to Michelle.
Going to continue to move the microphone down. I'm glad that I was not right after Clark. Yes, hi, I'm Michelle Harold, and it's been really great to be in this session hearing about some of the really exciting advancements related to RFS and MPAS, and we've seen a lot of really great verification. So kind of playing off on that theme a little bit, I'll be talking about MET+ and some of its recent advancements with respect to short-range weather application verification. And I want to give a big shout out to all the co-authors who not only helped with a number of the slides, but also the actual advancements in the MET+ code itself. All right, so just kind of an outline for today's talk. I know a lot of you have already heard about MET+ throughout the week, but we'll give a little bit of an overview on MET+, then kind of give a briefing on what MET+ can do for you with respect to short-range weather applications. But I will spend a bulk of the talk talking about some of the new features and enhancements related to MET+ in short-range weather application verification. And as I was putting my slides together, I was getting a lot of Alex Trebek vibes. So there's a little bit of everything that we'll be talking about today. So I've aptly named this the potpourri part of the talk. So we'll go over some of the recent enhancements, and hopefully there's something you can gain from that. And then briefly, I'll just talk about some of the future directions for short-range weather verification, and then end on providing some information on MET+ if you wanted to get involved in how we provide support. All right, so a little bit of background on MET+ itself. We kind of refer to it as a one-stop shop for trusted verification. It's a highly configurable verification framework, and it can span a large range of both temporal and spatial scales. So really going down to the warn-on forecast kind of scales all the way up to the climate scales. And we do also pride ourselves in being community-driven, so we have a number of active partnerships, both at national and international operational centers, universities, research community, as well as the private sector. And so with that, we do try and keep our code extensible and scalable with that. We also provide very active user support via GitHub discussions, so if there's questions that arise, you can contact us and work with us. And then we also have a number of use cases, which are kind of like recipe files for easy spin-up. So in the end, we hope to provide a versatile toolkit that can enable both objective as well as reproducible evaluations, again, over a very large range of weather and climate applications. But today, obviously, we'll be focusing more on the short-range weather side of things. So these are just some examples of traditional verification that MET+ can handle. So there's a number of grid-to-grid and grid-to-point type evaluations for deterministic, ensemble, as well as probabilistic verification, and spanning both single and time lagging. So these are just some examples of the type of verification that MET+ can provide. And MET+ is also integrated within the short-range weather applications, so you can do verification via the short-range weather app. I provided the GitHub link there. And so again, these are the types of verifications that we're currently and actively doing on short-range weather output. In addition to more traditional type verification, we also have a number of neighborhood methods, such as fraction skill score. So you can see an example of that on the left side of the panel. This is some of the verification that Mackenzie Larson presented yesterday, looking at some of the work we're doing with evaluating initial condition blending within MPAS. So looking at some fraction skill scores for composite reflectivity and testing out different weighting sensitivities. You can also do object-based verification within MET+. We have the BODE tool, the method for object-based diagnostic evaluation. And this is just some examples using it on hazardous weather testbed data back from 2024. But it can help kind of go beyond traditional statistics, where you can get things about the size of the objects, the intensities, and displacements and things like that. All right, so now going into our potpourri section, we'll kind of be going over some of the new features and enhancements within MET+ for short-range weather applications. First, I want to talk about some of the work we've been doing for verifying smoke and dust. So we've added some new verification data sets and capabilities that MET+ can handle. And this is all now verification that is available within the short-range weather app. So we've been working with some folks at GSL, specifically on some of the RFS prototypes to look at smoke and dust. So now MET+ within the short-range weather app can handle looking at aerosol optical depth verification using the AeroNet version 3 dataset. And then we're also using the AirNow dataset to look at verifying particulate matter. And these are just some examples from the prototype. So we did kind of set this capability up on a prototype from October of 23. And so you can see again some of the examples. And using that, we were able to integrate this into the short range weather app. So now there is deterministic verification, including the automatic observation retrieval, both from NOAA HPSS as well as AWS for processing AOD, PM 2.5 and PM 10. And then there are also some updates within the MET code itself for enhanced GRIB2 table support to handle those smoke and dust variables. In addition, you might not traditionally think you'd see tropical cyclone type verification in this particular session, but there was a really great case with Hurricane Idalia where since it fell within the RFS domain, we were able to apply some of our tropical cyclone verification tools to look at things on the short range weather side. And so this is kind of showing some of the new capabilities within a tool called TCRMW within MET, or the TC Radius of Maximum Wind tool. So this is looking at some azimuthally averaged variables. So this tool can basically take your data and regrid it to a moving range azimuth grid that goes along the storm track. So we have the specific humidity across the top for the HAVS A in the upper left and the RFS in the upper right. And then we also have the azimuthally averaged vertical velocity in the bottom panels. And so you can look at things like the depth of the moist layer with the specific humidity, as well as like the strength of the eye wall, things like that with the vertical velocity. Some really great tools on the tropical cyclone side of things, and so that area has also been exploding in MET Plus as well. In addition to that, a lot of the things I've shown already have been on the post-processed grid. So now MET is just kind of starting its foray into helping support things on the unstructured grid. So this really is an emerging capability, but we're looking to add on to this. So now there is some basic support for directly reading in the MPAS diag files. And so there are some caveats that I just wanted to share. It's currently only for variables at cell centers that are supported and only supports the nearest neighbor for selecting points or gridded observations around cells. And so this is just an example of using PointStat, which is our grid to point tool, on this capability. So again, it is emerging, but we do have some basic functionality to look at verification on the unstructured grid. In addition, in MET 12.1, there's a new tool called the PairStat tool. And basically, this is going to help with scoring already pair data. So if you have a forecast and obs of pairs, MET can then read that data in and write some output. The main thing that I wanted to point out about this is that it can fast track integration using MET with JEDI output. So if you have the JEDI matched forecast and obs pairs from the YODA data, it can read that in and then perform statistical calculations on that output. And then kind of ending up on just more of a technical note, we've done a lot of work in the past year or so a big shout out to our software engineers. They have put in the application of OpenMP throughout both the library code and the application code. MET is a lot of things, but it has been noted as being slow, so we have been trying to address that in the last several releases. And so those enhancements are now available in MET 12.1. And just as a note for those who've used some of our object-based verification and noted some of the slow runtimes, we have seen upwards of a 50% decrease in runtime for some of these applications. So these are pretty significant decreases in runtime that we've seen. And in addition to that, we now have an installation via Conda Forge. So you can get MET Plus via Conda Forge, which we're really hoping kind of lowers the barrier for people to be able to get it. We have also heard that it is not the most easy to install, and so we're hoping that this will address that. While it is supported on a number of HPCs, we realize that that's a smaller part of our user group, so we're hoping that having it available via Conda Forge will help increase the usage of MET as well. All right, so then I just wanted to briefly end on kind of where we're going as far as a unified approach, at least within the DTC, for helping accelerate and advance how we do our testing and evaluation. So as I noted, we have MET Plus within the Short Range Weather app. HAVS is also working on integrating MET Plus into the HAVS app as well. But we decided that instead of having verification live within each of the different and individual applications, it might be better to take out the verification, for example, in the Short Range Weather app, and have it live in an independent verification workflow that can be used and monitored by the DTC. And so we will be looking at kind of having a unified verification framework where we have a number of MET Plus capabilities that live within a workflow that can then be imported as like submodules in the individual applications. So that could be things for short range weather, HAVS, as well as global type applications. And we'll also be working with some AI-based statistics as well that we'll be looking to get into this workflow. And so finally, I just wanted to end with a couple of MET+ related resources. We will have version 6.2 of MET+ coming out sometime in October, so stay tuned for that. And as I mentioned before, we really do have a robust way of supporting the community via our discussions, GitHub discussions. We have an online tutorial as well. And then we're very active with GitHub, so you can monitor all the different progress going on with things like that. And so with that, I think I sped through it efficiently. I'd be happy to answer any questions or chat afterwards about your usage of MET+ or picking up MET+ for the first time.
All right, thanks, Michelle. We certainly have time for a question or a few for Michelle on that. Looks like Lou's taking it.
How to warm up. Is this on? First of all, I want to thank you for doing something in Conda. Okay, I think lowering the barriers, which is one of my themes you'll hear in a minute, lowering barriers to entry for people, doing that kind of install. I mean, I almost do everything now via Conda, NC View, NCO tools, you know, the whole thing. And I think that's a really great way. There's also the MPAS Conda environment. I'm going to ask a picky question. I noticed you listed Ricardo in that unified diagram there. Are you thinking about EC flow at all?
Potentially, and actually, I think, is Mike Kuvilich in here? I was going to, Mike is the mastermind behind this, so I didn't know if you wanted to address that, Mike. And if you could use the microphone, that would be great.
It all just comes down to demand and money that we have. The initial infrastructure was all tied to the short-range weather app, so which was Ricoto. So I know there are people that are kind of working with EC Flow and maybe making it easier to install, but we have no specific plans, I guess is what I'm saying. Much easier way to do it, I guess.
Yeah, thanks for pointing that out. Yeah, I think we're kind of workflow, task manager agnostic, whatever's the easiest. So, yeah, awesome. Thanks.
Leisha.
I wonder how you react to the presentations that we saw just before about the results of the spring experiment, saying that the subjective results are so different from the objective results. Does that mean we need additional verification metrics, or is it just a matter of us in our brain kind of, looking at a number of different scores?
No, and Leisha, that's a really great question. I think it's a little bit of both. I think it was Israel had mentioned he had shown some object-based verification that does match a little bit better to what we're seeing. So I think that the ways of traditional verification of grid-to-grid is kind of beyond us, especially as we move down to those more convective allowing scales, and we really do have to start exploring object-based or less traditional methods. So whether that's using the tools that we have better and trying to interpret and understand and set them up better, or developing other things. But I do think the days of looking at a simple POD are moving beyond us.
Dave, you get the last question.
Which actually takes me, one of the themes of this workshop has been a little bit with machine learning and AI, which is really good at vision type applications. Any plans to try to incorporate some of that, to really kind of address some of Leisha's question also?
Another wonderful question. So I believe it was at the DTC Science Advisory Board meeting last year. There was someone, MA was there, and she had shown an example of a TC that basically created like 2 TCs and was marching along. And so we started to talk about ways we could incorporate object-based verification or some sort of wavelets or something like that to get at more object-based type things, especially with AI applications. So yeah, we're kind of on the same page. We're looking to partner with experts. So admittedly, we're very good at verification. We're still learning a lot about the AI side of things. And so if we can partner with some of the scientists using AI, I think that would really help with how we kind of propel MET forward into the world of AI.
Thanks again, Michelle. Okay, so now we're going to pivot to our discussion panel. Before we do that, I want to give one more round of applause for all 6 speakers in this session. So at this time, I'm going to ask Kate, Lou, Christiane to come up to the stage with me for our panel discussion. I think we've got got Jacob Carley and Matt Pyle online, and I'm going to try to frame this a little bit before we go into the deeper discussion. So before we do that, basically the idea of this is to represent sort of a cross-section of the research to operations community and our interests, particularly as it relates to short-range weather and convective allowing modeling. There's a lot of barriers and challenges that we all are, I think, seeing the discussions of in various facets this week. We're going to do a little, like I said, deeper dive into some of those aspects, including some opportunities here in this discussion. So before we do that, I'd just like to have each of the panelists introduce themselves briefly. So we'll just go down the line here. Just let everybody know where you're from and the background.
I'm Christiane Jablonowski. I'm a professor at the University of Michigan. I'm a community co-lead of the UFS short-range weather application and mostly pay attention to the dynamical course and the dynamics within the UFS.
Thank you. Kate Fastel, I'm the Assistant Director of the Mesoscale and Microscale Meteorology Lab at NSF NCAR.
Lou Wicker, NSSL, OAR, and one of the leaders of the Warning Forecast program, and also on the CAM committee.
And we got two online. I think Jacob.
Hi, everyone. I'm Jacob Carley. I'm the Chief of the Engineering and Implementation Branch at the Environmental Modeling Center, also on the SRW CAM co-lead group.
Thanks, Jacob. And Matt?
I'm Matthew Pyle. I work for Jacob. Also help lead the RFS project and also part of the SRW CAM team as well.
Thank you. And so, like I said, I think we're going to try to stimulate some discussion here on the complexities of our software ecosystem for doing a lot of work in the SRW CAM arena, but also, again, wanting to bolster the capabilities of the UFS and be as agile as we can in transitioning capabilities into operations. So I think we're going to start with a research perspective and then go over to the operations perspective on this. So I'm going to kick it off with probably Lou to start with and say a few things about some of the first slides of this. And then I will also say this discussion may spill over into the plenary session after the break. I think there'll be some commonalities, and that's hopefully certainly welcome. And like I said, we'll see where the discussion goes. So Lou, why don't you start?
Okay, I guess I got to hold this down the whole time? Okay. I don't know. I'm not sure I'm that coordinated anymore. So can we go to the next slide? So as usual for me, I like to be a bit hyperbolic just to sort of make a point. I not necessarily believe everything to the last minute here, but on the other hand, we were supposed to do stuff to stir discussion. So I wanted to talk about current challenges to doing Agile R2O and O2R for that matter. I think we have a lot of complexities in the system. We are trying to do complex things, and I don't think that we can minimize the fact that we're trying to do hard things. But I think we, so let's see, I'm supposed to run the thing here? Okay. So I put down some ideas, which doesn't, oh, okay. So, no, of course it's delayed. Let me go back one. Okay. So I've complained about this before at this very meeting a few years ago. I'll still complain. I'm getting old, so I'll tell you to get off my lawn too. So I think the software stack is very deep, and I know that a lot of people have worked very hard at Epic and other places to make it work as well as they can. But I think that in some respects, our approach to some of these problems could be a lot more coordinated and probably thoughtful. I do think, as a big organization, we have a lot of things going on. The first thing is we have a lot of HPC resources, but for various reasons, every system is set up differently. One of the things that this is also relating to some of the stuff with JEDI as well. Containers are only supported on about half the systems. Why? Well, I'm sure there's reasons why, but that means other people have to do other work to support the software in a different mode than containerization, which can actually simplify, as I think many people here know. Cloud support, very limited beyond AWS. As many of you know, Warning Forecast runs on Azure for an interesting story there a long time ago. There are other barriers, and this is what I was sort of talking about before with Met Plus, that simple things like what compilers can you use? It turns out that some aspects of our systems, including JEDI, don't compile with GNU. And then if they do compile with Intel, you have to get the 2021 version, which isn't probably allowed in a lot of systems. So, you know, in terms of doing research, we need to get access to the right resources, but then it's even then sometimes hard to get going. And then there's a lot of R&D user challenges, packages, submodules. There's nothing wrong with submodules inherently, but the sort of what is the quality of all these organizations contributing to the submodules? Is documentation even? Is user information even? I've had an interesting use case, as Leisha said earlier this week, with a user of MPAS. So development is kind of hard when you have to do it in teamwork all the time, and I'm a little bit old school where a lot of the stuff that I did and we did was with a very small group. So, and then we get back to how are we going to test our systems with continuous integration and continuous development, and what resources are we going to have? I'm not just talking about HPC resources, but what about people to handle pull requests and evaluations and testing, and does code meet standard? These are all real challenges. And I'll go to my final slide. So I think that we need to balance the complexity, with the resources. And I think NOAA needs to think about, and the OCOI's office and all that, to really think about how we can limit or how can we simplify the workflows in all of these systems simultaneously. Sometimes that may be engender taking more risk, I don't know. But it also will help other organizations like EPIC not to have to support 40 or 50 or 60 different situations. We have mounting technical debt, and that essentially gets us behind the 8 ball. And I'm not going to read every one of these. We need to improve our tools, and we need to have standardized build tools. And what I mean by that is pick things that everybody can download at night at 10 o'clock when they're trying to get something done. I know that sounds a little bit optimistic or maybe even unreasonable, but that's a lot of how this work gets done, especially off NOAA resources like at campuses and universities. People work at weird times and they get into these barriers and they can't always wait. I think that we need two new ways to isolate particular pieces. I think the hierarchical testing framework for the UFS and the physics, I think, is a really good start in that example. So my final thing here is that, you know, we need to have complex systems, but we need to be able to work these systems in as simple as possible scenarios, i.e., I think the reason why a lot of people work in the standalone MPAS is because it's easy to stand up and work with. We need to think about technical debt. I know that Jacob has been educating me on this particular aspect of things. And I really think that there's an advantage to everyone in NOAA to having both a community standalone, if you will, MPAS, and the UFS MPAS to attack the problems with the right tools and not assume that we can use one tool to solve all things at all times. So I'll end there.
Thanks, Lou. So plenty of food for thought there. Again, I want to swing over to the operational side of the spectrum here for the perspective on things from Jacob. So I'm going to turn the floor over to Jacob, and then we'll open it up for broader discussion here.
All righty. Thanks, Lou. Thanks, Curtis. I think a lot of what you presented, Lou, definitely resonates on the operational perspective side of things. Obviously, we're doing development as well. I think that food web diagram you showed of the UFS clearly shows, I think, what's known in sort of the software engineering world as a highly coupled architecture. In other words, what that means is if you change one thing, you're changing everything. And that requires a whole boatload of testing across the entire integrated ecosystem anytime someone wants to make a PR. So we see that in the form of stuff taking a little while to get through the pull request queue in UFS weather models. So we need to do what we can to decouple the applications there. And there is work that's ongoing right now from EPIC that's exploratory and finding out ways to do that. And I think that's an excellent step forward. So thanks for advancing the slide there. So what I really want to talk about also, and it's all tied together, is some of the issues that we currently have in the development and operations lifecycle. So there's sort of three things here. But I think we all know that the current life cycle that we have is slow, risky, and outdated. So the first thing I want to call attention to, and if you were at the R2O panel session earlier today, this is going to be a little bit of a repeat, but I have a platform for a soapbox here, so I'm going to use it. When we work on our development, when we do development for operational implementations, we plan them based on anticipated scientific innovations. But the progress toward those innovations is not linear. It's very hard to anticipate when you think your innovation is going to come to reality, it's going to bear fruit, and it's going to be ready to go into an operational system. That takes time, and there's always some slack in that schedule, or some slip in that schedule where scope needs to be changed, something goes out of an upgrade, something comes into an upgrade, and schedules move. And we end up in a situation where we go by, we have several years between implementations. And so what we have right now is on the left, this is actually a snapshot of the production suite. It might be a little outdated, actually. Hopefully this is on a large enough screen in the conference room that the complexity is conveyed pretty well. But that little circle in the middle there is the global forecast system. Everything in the production suite pretty much depends either directly or indirectly on the GFS. And so just imagine the amount of downstream testing you have to do when the GFS is changed. So we can think back to the UFS food web diagram that we saw, where I mentioned, changing anything changes everything, and you have to do a lot of testing to make sure that nothing breaks. Likewise, when we're trying to make changes to our production suite, we also have a highly coupled ecosystem there, where changing anything in the GFS changes everything. So this is a situation that we need to slowly work on decoupling and coming to terms with. But we also have a challenge in terms of how we've framed our development and implementation lifecycle. So we have this waterfall approach where we plan based on anticipated scientific innovation. When we think all these upgrades to our convective parameterization, our data assimilation, our products, model dynamics, what have yous, will all come nicely together alongside the infrastructure that needs to support that endeavor to get it done. And so what ends up happening is this little cartoon guy, which is, I'll just say it's me, falling down the waterfall development stairs. It's not fun, and it doesn't have a comfortable outcome. And what it ends up leading to is this guy on the right. This is, of course, a Gemini generated figure. The prompt was something like a really frustrated scientist who's debugging and can't get code to work, and there's delays. So there's steam and smoke coming off this person, and questionable things, and what looks like an Erlenmeyer flask sitting next to him. Anyway, you get high risk, burnout, delays. It's really hard to keep pace with progress. So next slide, please. So the question is what do we do about this? So Agile is very buzzwordy, and I'm going to use it as a buzzword here. But there are different approaches that are established best practice in the software engineering community that we can adopt to, I think, to make our lives a little bit easier and make progress more quickly and deliver scientific innovation on a more regular cadence. So right now we have a situation where we deliver upgrades every 2 to 4 years. Our stakeholders get frustrated because they have to wait 2 to 4 years for an upgrade. And then if their priorities aren't addressed in that upgrade completely, because maybe that anticipated scientific innovation just didn't come to fruition and needed more time, then there's just a lot of frustration that comes in with, well, it's going to take another 2 to 4 years to get that issue fixed, right? Well, if we can separate the innovation, that upgrade cycle, from anticipating when things are going to be ready to just pulling in what's already ready today, if that makes sense, packaging that up, and then conducting our engineering testing cycle on everything, and then performing an implementation based on predetermined cadence, we can still fold in all the innovation and all the upgrades that we want, but deliver those to the field, to the community in an operational context much more quickly. So instead of waiting for things to be ready, we pull them in as they are ready into a variety of packages and releases. What we also need to do is bring development and operations closer together. So I would love to get rid of this whole process of hardening code applications and revising things based on implementation standards, then transitioning into operations. There's a lot of rework and stuff there that doesn't need to be done. We should bake that into the development process. So update our continuous integration process so that we have tests and we have checks that say, okay, does your code meet standards? Is everything aligned? And then yes, if it does, it goes in. That eliminates a whole bunch of extra work that we have to do at the end that introduces a lot of risk in our schedule. So bringing those environments closer together, and I just mentioned one way. There are many other ways to do this. Lou mentioned containers. I think that's an excellent idea. So I think bringing these concepts of, and some of you may know this, but this is diving more deeply into the idea of a DevOps framework, I think can enable us to have more rapid innovation and less mounting risk and burnout with these giant implementations. So doing things a little bit more incrementally will help us keep things maintainable and sustainable over the long term. But it also requires that we develop and invest in the tools and the infrastructure to manage this stuff appropriately, that we spend the time that we need to spend on reducing the technical debt, like Lou mentioned, and investing in a testing framework and going through all of our codes that our weather prediction codes and weather and climate prediction codes and all of our couple modeling codes. A lot of them are pretty old, and not a lot of them have unit tests built into them. So we're going to have to build in some of these extra testing frameworks. And we need to have time and resources to do that, to enable that framework for that rapid innovation. So I think this is my last slide. So I'll kind of leave things there. Thank you.
Thanks, Jacob. So I want to, like I said, invite some thought and perspective comments from the audience here, but I'd also open it up for other panelists who would like to make any comments about your perspectives, particularly on the research side and the accessibility to UFS codes or other aspects of the experiences you're working on with your research. So,
yeah, maybe just a few words. Yeah, from a community user perspective side, I think it's crucially important to have enough documentation and portability, and that's of course a big issue for the current UFS, and that's what Lou addressed is really an important and pressing issue for the university or broader community, especially also the use of HPC. Universities don't typically have access to NOAA facilities, so if we're lucky we have D-ratio, but it's not even designed for NOAA products, and it's very hard to even port the code over. Containers will help. But I think from a user perspective, also, yeah, bring the models up to standard in terms of usability, documentation, and also I'm, on the university side, I'm very willing also to then spread the word and educate the young folks about those models.
Thanks. Kate, you want to speak?
Nothing major to add. I think I actually really like Christiana's perspective from the university community and to represent most of the research. I think maybe one comment I'll make just to think about, Jacob, did you call it a food web diagram, or what was the component web?
Yeah, food web or something like that, yeah.
So one thing that strikes me with that particular graphic is that it really highlights the technical complexity, but also within each of those boxes and that web, there's a lot of competing priorities and owners of those research codes and missions, and it's another component to the technical complexity that's there.
Okay. Thoughts, comments, questions? Dave, you got your hands up, so just got the microphone.
So a lot of the things that were said really resonate with me, but part of as we're thinking about the hierarchical framework is as we're developing these tools, one of the things we need to be able to do, because in the end we want to be able to compare to observations to actually show that we're making a positive improvement. But right now, running the entire short-range weather app is very expensive, especially if you wanted to get the data assimilation, which is critical to actually getting to the point where you can compare to observations. So at some point, for development of modeling systems, we need perhaps a simplified DA framework that gets us initialized in a reasonable state. And I would love to see that somehow being developed or considered in this. How do we get, so you don't have to run a really expensive DA system, which is hard to do, hard to set up, workflow in itself is challenging, but can still get us initialized well enough that you can get to a good point to test your physical or chemical innovation. So it's more of a suggestion. I don't know if there's any thoughts on how that could be done, because part of it's getting the data. Part of it is Christiana's comment about getting it on a machine that works. and access to that machine. So there's a lot of challenges even getting to that point.
Oh, I agree with you, Dave. I've got a project that I'm teaching data assimilation to an NRC postdoc, and we're using an old Python LETKF code with CM1, and it's a very simple framework. And, you know, she's really fantastic young researcher, and she learned it, you know, in a couple of weeks. So I think that's the kind of thing where I'm not advertising this software. What I'm saying is I do think there's a role for that. It's just hard. I think we can't. I think we talked about this the other day in one of our meetings, that we can't do everything. And so what are our priorities and what are our resources on this? And I do think that maybe, I do think that there are tools that we have now that 10 years ago we didn't, like with GitHub and things like that. And if people would, I think there's stuff out there, there's a lot of stuff out there, it's just that nobody knows about it, it's hard to find. Or if it is hard to find, it's hard to use. And so I don't know there's a good answer to that, other than I agree with it, so.
Looks like Maui might have a response to that. And then it looks like we got Legia also coming up for a question. So Maui, you want to respond?
Well, I was hoping that the cadre PIs can be here to respond to you. I know that they are drafting a BAMS paper specifically about how to teach DA. All right, so they are funded for that purpose, but I want to be very brief. In this first year of the cadre workshop, Epic team teamed up with cadre PIs to deliver a UFS land DA system. The idea is that we're not going to focus on workflow. Any workflow should be fine, but as long as we make sure the model and the JEDI configuration builder, as well as the JEDI version itself, are consistent, then we are more or less, we are probably 80% consistent with the operational system. And any operational hardening should be Jacob's job. That's my opinion. So I'll throw it back to Jacob.
Thanks, Maui.
Just a follow-up on that.
Yeah.
So this doesn't attack the DA problem, it attacks the initialization problem, which is very important for the short range, is that what we're doing in the global is using the methodology of replay, where it's like a centered nudging to an existing analysis, but you let the model basically develop the details. We're doing this actually with a nested model, and we're nudging to error 5, quarter degree, but the model is retaining the fine structures still. So it's a good way to test the model itself in an initialization way without having to carry the DA.
I'll add one last thing on the DA front. There are analogs to the hierarchical, single column model in DA framework, single ob tests, where you can deconstruct the complexity of a DA system down to looking at ob's impact from assimilating a single observation. So there are tools there, but again, some of the stuff is buried in the complexity of the software, and that's where I think we have some of the challenges. Jacob.
Yeah, so two things. One, I want to pivot over to Israel because he's been very patient with his hand up. But I got to address the comment from Mao Yi, though. Operational hardening, I think, is not something that we can say is one person's responsibility or another. I think it's all of our responsibility. If the end goal here is to deliver innovations that have benefits to operations and improve the forecast for everybody, we can't be in a situation where we say, that's not my job or that's not my role. I think it's really important that we have clearly articulated coding standards and practices in place that people can follow easily. It's not hard to find. And then continuous integration framework that checks that for you so that you're not having to rely on a person that's in between you and your PR going through. It's just automated linters and checkers that go through and say, yes, it's good. No, it's not. Here's what you need to change, fix it. It's at the end of the day, it takes a couple minutes and you're done. And just by that alone, I think will lower the barrier to entry considerably across the board. And I think it'll bring us closer together as a community. I think it's in everyone's best interest. And frankly, it's, our job to write good quality code, especially for purposes of scientific integrity and reproducibility and those sorts of things. So that's my piece there. Thanks. All right, Israel, go ahead.
Yeah, thanks, Jacob. I did want to respond to some of Jacob's comments from a forecast user perspective. Believe me, I'm all for agile development and, rapidly advancing the science. However, I do want to caution, if we get into too rapid of a changing environment, it's very difficult for forecasters to adapt and adjust. And what version are we looking at? What are the characteristics? How has it changed from the last version? So I think there's probably a happy medium. If you're changing the models every year, the forecasters are not going to be able to keep up and understand what they're looking at. Of course, in our current framework, it's probably too slow of a development. So there's probably some happy medium in between there.
Just to add a brief comment to that, is there any way we could develop kind of two different release cycles in parallel, similar to, I don't know, if you're familiar with a system like Linux and or Ubuntu, how they release, where they'll have a long-term support, kind of stable version and then experimental versions throughout to offer both, the option of a more stable version and rapid development? Is that something that could be done?
Yeah, I'll say, I mean, we kind of do that already, where we have real-time parallel versions that we make available to certain highly engaged stakeholders. It's out there in the public. It's just, you'd have to know what the link is to find the information and stuff like that. The test beds are a great example, where we, share earlier versions of our R&D systems. We did this all the time with the RFS, and we've done it with other systems as well. So we can kind of get that early feedback, early look as well. So we do kind of have that approach now, and I think that's an approach that we want to maintain going forward, because I do think it's pretty effective.
Thanks, Jacob. Back to the room, Leisha.
Israel already talked about what I was going to ask, is how much have the forecasters been involved in this new paradigm of agile implementations? I'm really excited about the agile implementations, but how can we, have forecasters engaged with models that change characteristics, and how are we going to overcome the long process, not just from the field evaluation, but also the NCO evaluation? I mean, yesterday we saw Sergey Frolov's presentation on AI and how agile NOAA has been in implementing Eagle. Yes, but Eagle has no downstream applications and doesn't replace anything. So in a way, that's like the easiest case. But if you're going to replace, say, the GFS, there's a lot going downstream. So I'd love to have more discussion. I don't know if this is the right place, but how do we involve the forecasters there?
Go ahead, Lou.
Well, I agree with you that this case for the partnership we have with OSCI and moving WAFs into the operations or near the operational setting. I mean, we've been able to shorten that road, I think, by years. And there are challenges with doing that right now where I know that there's an effort to push WAFs from this sort of experimental VLab case where we just sort of handed over to OSCI to look at and run for the Weather Service now into operations in a year. So I think there's a lot of challenges. We've already hearing about them. But I think that we're just going to have to keep pounding on the doors a little bit. And I think change the paradigm, as I think Jacob's talked about, where things are a little bit more operational ready by the time they hit the door at NCO. But I think and I think the real challenge is going to be is how do we deal with things that maybe should run on the cloud versus on-prem and things like that. But I think everybody knows that we need to be faster than what we are now. And I agree also that too fast is going to mess things up as well, which actually concerns me about some of the machine learning applications that may be able to come out with a new version of the model every year. And if it has significantly different behaviors than the previous model, I don't know how we're going to deal with that particular situation either in the operations. So.
Thanks, Lou. It is 3 o'clock, so I hate to stifle discussion, but technically we are now at a break. That said, if there are more questions, I would recommend adding those either to Slido, or I have a suspicion that these threads are going to continue in the plenary session that starts at 3:30. So you'll have an opportunity, I think, to continue some of these aspects of discussion then. So thank you. I'll turn it over here for last announcements.
For the Mesa Lab, there we go. The shuttle for the Mesa Lab tour will pick up people at 3:05, so if you're trying to catch that one, run, and 3:35 for the 3:45 tour of the Mesa Lab. Additionally, we did forget to do the raffle before lunch, so that will be happening at the end of the day. But otherwise, enjoy your break, and we'll be back at 3:30.
We thank everybody again.
Just going to give a minute for folks to filter into the room. In the meantime, I will give a quick weather update. Scattered showers and thunderstorms continue with a mesoscale discussion off to our northeast, although unlikely to result in a watch.
Are you okay?
Yeah, I'm
Okay.
fine. It actually is not hurting bad right now.
All right, I am going to go ahead and introduce our session chairs. And this session is the MPAS Collaborations and Community Engagement panel. Our chairs are Kate Fossel, Jeff Beck, no relation I'm told, and Catherine Newman.
This whole thing of holding it down is like.
All right, thanks. We'll go ahead and get started. This session will explore ways to foster collaborative efforts and strategies for advancing MPAS in the community. And we have panelists from both NOAA and CAR who will be speaking to this. So we've heard a lot today and throughout the week about the adoption of MPAS in different NOAA applications, and this effort's been possible in large part through the collaboration between NOAA and NCAR. And as Everett mentioned in his opening remarks earlier this week, trust is key to successful partnerships. And trust has been key to the growth of MPAS through partnerships between NCAR, NOAA, and the community. However, much of the future development of MPAS, including, for example, MPAS in the UFS, will require contributions from diverse stakeholders and community partners. In addition, many development efforts won't happen overnight and can't be completed by a single partner. So we're hopeful others in the community will engage, hopefully with EPIC helping to facilitate. Therefore, it's critically important that we encourage and facilitate pathways toward community engagement and development, which is necessary to expand the adoption and success of MPAS. So we invited our panelists here for a discussion to continue conversations about MPAS collaboration and community engagement. And with that said, the panelists will now introduce themselves and we'll have a few questions to kick things off. But we encourage participants to bring forward questions to the panelists to hear what's on their mind from the community as well. We'll go ahead and start right to left, I guess.
I'm Bill Scamrock. I'm a senior scientist in the Mesoscale and Microscale Meteorology Laboratory. I'm lead scientist for MPAS. I can also say I was in the room at EMC back in 1997 when it was in Camp Springs, where we kicked off the WRF development as a joint development effort. So I've seen a lot, not all of it, but a lot. And with that, I'd like to begin by noting that our development, our move from WRF to MPAS is accelerating. And in WRF, in terms of engagement to the community, we essentially brought in anything the community brought to us, which was both a strength and a weakness. But however, at NCAR, essentially everything was internal in terms of bringing that in. Community members would work with us, but it would come into our repository. We controlled it, and it was a community model in that we supported it to the community. With MPAS, we are trying to move to a true community development paradigm. As you've heard, although not, I think, in much detail, but we're bringing the physics from GSL and NSSL and others into MPAS, but we're doing this by pulling directly from their repositories. So MPAS is going to become a community model first and foremost, in the sense that the components are going to come from the developers in the community, and we're going to pull them in from their authoritative repositories. The second thing is that we're looking to expand how it's governed and bring our major developers in as collaborators in that development, in a development committee, and expand the governance and decision-making to include all the major developers that we have. NOAA is absolutely a major developer, as you've seen with the RFS implementation in MPAS with one on forecast. We also have applications that are in development lines in NOAA that span from global down to LES that we're working with them on. So there's a lot going on there. There's a couple of other things I'd like to just mention here in terms of the community release of MPAS development that does overlap with folks in NOAA, but also a lot of other places. You've heard a lot about JEDI running with MPAS. The first operational implementation, although operational in the private sector and the weather company, is already running MPAS and JEDI. So, and we strongly support that work, and we're doing development in-house, both in MQ, but also with our collaborators. And we get a lot of support from the Air Force for this and other operational centers that want to use it in other places in the world, a big component in Asia, for example. The other development I'd like to point out is ChemPass. You remember WharfChem? George Grull is right here. He was gracious enough to put me as the last author on that WharfChem paper, and that is the most cited paper I have. And what it also means is that the chemistry community was the biggest community in WRF, and it's important that we move forward to satisfy the needs of that community. And we're doing that in the development of what we call ChemPass, and that's a development that's joint with NOAA and a number of folks at universities, being led in NCAR through ACOM, our chemistry laboratory, where we're bringing together the components from their Musica system, but also from CATChem and NOAA, and some outside contributions to move that forward. So will be a big advance for us. And we just got some extra money from NSF, from an NSF grant, so I think that's got traction here at NCAR, and it's going to help a lot for our collaborators outside too. Other development efforts you should look forward to. There will be an LES capability in MPAS that we are testing internally and that we're looking to test with partners that we hope to release somewhere before the middle of next year. We're already running idealized tests with that, and we hope to be testing some real data cases soon. We're going to be releasing GoCart, essentially aerosol and simplified chemistry model, hopefully before the end of this calendar year. We have GPU capability that's being developed, and we're looking forward to partnering with NOAA and other physics developers in particular, because that's where the big gaps are right now. The DICOR is moving forward with a stable, supportable GPU port, but it really is the physics we need to move forward. And I should also mention that there's efforts in urban modeling in a number of our collaborators, and along with model coupling efforts that are ongoing. That's an interesting problem in its own right in terms of the complexity. So I had conclusions here which talk a lot about what we heard in the last session, that our needs are evolving rapidly. We have to better leverage our collective development efforts. We have to be more agile in all the meanings of that word there. And we have to lower our barriers to bringing in new advances to our system. So you heard a lot about the last session, and you'll hear more about it here. So I want to close with the development, the evolution of our governance of this model to be a true community collaborative development and paradigm is, I think, a critical step forward for us to evolve to a system which can keep pace with our research and ultimately operational needs.
I'm Christiane Jablonowski. I'm a professor at the University of Michigan, and I serve a couple of roles for the UFS. I'm also a community co-lead for the UFS short-range weather application, and of course that's currently built on top of Rufus and FE3. My research, though, is really in the dynamical core world, similar actually here to Bill's comment, but I'm framework agnostic, and that means I look at MPAS and also other DICORs, FE3, in all kinds of environments, for example, in the UFS, in the community atmosphere model here at NCAR, and also MPAS standalone. And I pay attention to features like, is it usable? Is it user-friendly? Is it documented? And I bug Bill with questions, actually, and make suggestions to make it an even better product. I see my role in various ways. I'm an educator, so I bring MPAS and other models into the classroom. We just did that here at NCAR, for example. This summer, we brought here 50 students and postdocs, and we ran an event called the Dynamical Core Model in a Comparison Project. If you haven't checked out my poster, 22, if you like. So there's a group of all of us testing for a week models like FE3 dynamical cores, like FE3 MPAS spectral element dynamical core from DOE, and also even the UK Met Office one. And that really exposes another element that I want to bring to the table, because we often even use idealized configurations, idealized test cases, and we really build up test beds actually to make statements about the pros and cons of the dynamics without even physics, to immediately have a really honest look at dissipation properties and other features, the numerical features of the dynamical cores. So this is kind of my role here. I bring to the table a really different look at MPAS and other models and bring them into the classroom.
Hi, my name is Lou. I'm an MPAS user. So I'm Lou Wicker. I'm the chief scientist of the War-on Forecast program at NSSL in Norman. I've been a partner in crime with people at NCAR, especially Bill, since the late 80s, developing models and capabilities. My interests, I've had a front row seat, sometimes sitting on the sideline, but in the corner on the front row seat, but also to model developments and model changes in NOAA in the last 10 years and the processes involved with that and the challenges involved with that. I'm looking forward to trying this regional redevelopment again, and hopefully to provide some perspective and some assistance in trying to make it work for NOAA and for the large community at large, or the university community, in ways that I think could really improve forecasting for not only for operations, but also new research opportunities with variable resolution meshes and things like that. So I have an obvious interest in operational prediction, severe weather prediction, but I also have a strong interest in rooted in a background of storm scale dynamics, tornado dynamics, and things like that. And one of these days I might even get back to it. So, yeah.
All right. Well, my name is Ligia Bernardet. Like Lou, I work for NOAA Research, but I'm based here in Boulder in the Global Systems Laboratory. So this is the laboratory that's well known for having built the RAP and HER operational models using the Warfare W. So we're very excited to be here at the cusp of building a new capability for NOAA based on MPAS. Bill, you were there those early WRF days of NOAA, and I was part of the DTC, the Developmental Testbed Center, and did the first tests for operational implementation of WRF at NOAA. So this sounds very familiar and very exciting. In my role in the GSL, I lead one of the divisions where we develop physical parameterizations and also atmospheric composition capabilities for models. So I'm very excited to bring new capabilities to MPAS and partner with NCAR in bringing this new physics that can help not only NOAA and its forecasts, but also the entire community, as this physics and capabilities can be distributed to the community. I'm also in my division in GSL, we have a scientific computing branch where we do a lot of work in advanced technologies, including GPUification of codes. And in that sense, I'm also excited to see what capabilities we can bring to MPAS, in particular, advancing the GPUification of the physics. So I'm interested both in the MPAS standalone going forward, but I'm also highly involved with Dustin Swales and others in NOAA in bringing the MPAS dynamical core into the UFS weather model, which is yet another way of bringing MPAS into the UFS. So ultimately, I'm really excited about being able to create these capabilities for research and operations, and I hope we can get some feedback from you guys today about how it would be most helpful to do that.
All right. So hi, I'm Catherine Newman. I am the Deputy Director for the NCAR node of the Developmental Testbed Center. The DTC is a partnership between NOAA, NCAR, and the Air Force. And the primary focus is on testing and evaluation for research operations and engaging the community in that process. So within the DTC, we have a number of exciting activities that are currently funded by both NOAA and NCAR that are focused on MPAS in the areas of CCPP, MET+, the stochastic physics, and general testing and evaluation with a focus on the standalone MPAS. And through that, we are building some great connections with the community and really starting to engage with some exciting efforts. I also wanted to just comment on the fact that when the DTC originated, it was all of the partners were working with WRF. And over the years, the different partners have taken different paths in their modeling efforts. And it seems at this point, there is some convergence back around MPAS. And so that's a really exciting point for us to be back kind of at this point where we're all working towards some of the same goals. So, yeah.
All right, thank you all to our panelists for the wonderful opening remarks. My name is Kate Vassell. I'm the Assistant Director for the Mesoscale and Microscale Meteorology Laboratory at NSF NCAR. Because I love Leisha and Bill so much, in 1997, I was in 7th grade. So as Jeff mentioned, can we take that off the record? As Jeff mentioned, we're going to kick off this session with a question that we've posed to the panel. But I also want to mention that in the previous session, the SRW app parallel session, there was a lot of really stimulating discussion around agility to R2O, which really fits into this discussion as well. So please come up to the microphone, ask your questions, or in Slido, we have a Slido rep. Please, let's have this be a discussion. Okay, so for our panelists, there are a number of organizations, labs, programs involved in the use of MPAS in UFS and in research and operations, each with its own mission and priorities. Would you share an example of where we're already working together and that has led to success? Feel free to raise your hand for who wants to go first. Go ahead, Leisha.
Well, we already mentioned that before, but I think what we're doing in physics is a big success. So what we're doing is we have a lot of physics that's whose development is led by GSL, right? So MYNN, boundary layer physics. Now we have TEMPO, which is a successor to the Thomson microphysics, etc. Those are physics that were part of the RAP and HERB models. They have been vastly used in the WRF community, and that we also want to use in MPAS. So we have a variety of host models, both MPAS as well as the FE3-based UFS, that want to use the same physics. And we have worked together to create a code management system in which the same basic code base can be served to a variety of host models. And this is technically perhaps not so challenging, even though it's a lot of work. I think the challenging part is the programmatic and collaborations, and we have advanced tremendously to put that in place, and it is a success. I think we see today in the forecast that Clark Evans showed in the previous session that MPAS with those physics is performing very well, and we will see this physics going out the door with the next community release of MPAS, or I believe that's the plan. So I think it's a great collaborative effort.
So I could go back 20, 25 years and talk about the collaboration between NCAR and NSSL and in the hazardous weather test bed, and then the subsequent development at GSL. But I'll talk to something recent, which I think is really important. As many of you might have heard, NSSL Warn on Forecast system is going to transition from a WRF-based system to an MPAS-based system. And There have been some challenges with that. We're overcoming them. Was not as smooth as we thought, just because it's a newer model and it has some different ways of doing things. And I think one of the best parts of one of the most useful parts is to have a collaboration where when we see problems in the model, that we can come to the developers and go, hey, there's something wrong here. And Bill's kind of a stickler. He's from the show me state, it must be somewhere, because he wants to really see some evidence. And as many of you know, I'm pretty hyperbolic, so I say, this is, crap, we got to fix this. And he's like, what do you mean? But I mean, I think the interaction between the developers and the people who know the code and the application developers like us, SSL, is a very vital link to actually enable rapid progress. And I think this has been the case in WRF, this has been the case, and it is the case in MPAS, and I'm looking forward to seeing where it goes.
Does anyone else want to respond to that question? All right, I'm going to take a pause and look to the audience. Please come to the microphone or post a question in Slido. This is your show too. We'd love to hear what is top of mind for MPAS or collaborations in general.
If I can ask one follow-up. Oh, I don't know if that's working. I'll speak loud. One follow-up to that. What processes have you found worked best for collaborating between, NOAA and NCAR on this? Like, you said you've got 25 years of experience. What have you found worked? What doesn't work? How can we improve that?
So, I don't know this too. I do think we have an advantage of having a long relationship, and I think that not everybody has that. Very few people have that, I think. On the other hand, I know that the NCAR staff and support developers are very open to talk to people, and NPAS WRF workshop happens every year. People come and bring problems. I do think one thing that I'm concerned about, and I know Bill is that the investment in modeling, people who know how to build models, know the inner workings of models, know really how to take apart the car and put it back together and make it run, is not something that we have invested in this country in very much in the last 25 years. So one very big concern of mine as I sort of reach see the end of the tunnel in my career, and others like us who were brought up in an NSF environment which supported model development and the first community models, I am concerned about how not only to maintain access to our information base and what our knowledge base is, but how is that actually going to be extended in the future? And I think that's even under more, and maybe it won't be important, but I think it's real under threat even more as more and more people then move to machine learning methodologies, which are equally valid and equally useful, but they're a completely different base. And I think that this narrowing of information, this restriction of skill, I think there is more in Europe. If you go look at the PDEs on a sphere, you see a lot more development and investment and student understanding of details of model in Europe. I mean, I actually think that's a crisis that's going to hit this country soon. And I think we needed to have like a crash program bringing people in to learn how to do things and bringing their stuff over here because they have good ideas. But as far as you're saying, I think we just need to make sure that we have consolidated lines of communication in forums and things like that that are not just NOAA, not just NCAR, but they're for everybody. And so they're sort of a more centralized repository of knowledge and experience that people can access.
I think there's two things. Well, one is programmatic, right? So recognizing that our missions are different, but also that there are synergies and that, things can work both ways. We cannot just pull the scale too much to one side. So when we develop the model, it has to have research capabilities. Otherwise, it's not interesting to the research community, but it must be efficient, run fast, and, have things. So programmatic, we have to organize ourselves, and then technically, there's a whole aspect of code management to support that, right? So I think we have been very successful in maintaining our code bases unified as we went forward with UIFCW and the HER development, and that has been a key way to support the collaboration.
I'll just mention that within the DTC, we have joint teams that have both employees from NCAR and from the NOAA labs, and those teams are integrated towards the same deliverables on many of the projects, and we have weekly meetings, and so being able to work together in that mode is I think really fruitful. And in each of the different organizations, a lot of our staff also work on projects that are outside of the DTC, so we can kind of bring in that expertise and some different motivations from our home institutions and then bring them back to these joint projects. So I think that's been really successful.
Anyone else from the panel? Go ahead, Christiana.
You brought a really important point, Brian, what maybe is still a challenge, and now I'm using my hat here from a community, outside community, not a NOAA or NCAR community, but university community, and I'm coming back to the usability of models like MPAS, and even the difficulties as from the outside community to just get them installed and going in CAM, in MPAS standalone, in the UFS. So the switch of frameworks and also workflows is indeed a challenge actually for the outside community. That's independent, of course, of MPAS. It's not just an MPAS problem, it's a generic problem, but the user and research community needs usability.
All right, any other questions from the audience at this time? There was a line in the last session. I know you have thoughts. I don't see our slide overs in here. Mike, go ahead.
Okay, I'll just reinforce what Lou said. We have an awful lot of people in the scientists that run the models, but we need people to open the hood and really see what makes things go and where does it go awry. And I think there's a lot of us working together on making sure that we can understand all those pieces because they ultimately add up to a global model, say, or a regional model, or a high-resolution model in a subdomain someplace. But the idea is we need to lift up the hood. And since I'm from Boulder, it's an electric car, okay? So just had to say that. So, but yeah, that's the machine learning. Great. Yeah, anyway, I was just gonna reiterate that, and we need to think about that. I know Christian Jakob, who's a colleague of mine, he's from Australia, but he said we have a lot of people that run the models, and it's great, and we find out what's going wrong, but we need to be able to tear apart the models and understand where they're going wrong. So.
Thanks, Mike.
I have a question regarding the use of MPAS for climate simulation or research. Basically, I want to know how long, for example, MPAS, for example, successful story or simulation for climate change, really extremely like El Nino, La Nino cases, over how long we can success time period, for example, 1 year, 2 years, 3 years, have success cases, demonstrate the capability of MPAS. Very clear?
I would have to say that we really don't have much to say about that. That there have been people who run it for long periods of time. It stays stable. I think the success is in the eye of the beholder there. And the physics we use, understand, was developed for NWP largely. So, and it's been run primarily not in coupled mode. There have been some runs as a dynamical core in CSM. It doesn't go off the rails. But the community release it's always got the ocean, the observed ocean temperatures to keep it in line. So I think we need to be looking at this a lot more. There are outside organizations that are looking at using MPAS for climate. Singapore's one, for example. The Taiwan and the Central Weather Agency and their groups that are related to their climate prediction are interested in that. So I think we're going to see a lot of development along those lines in terms of climate prediction at various scales.
The reason I'm asking the question because the industry need or interest of like a commodity trading power perspective. We're looking time horizon, 1 year, 2 years, 3 year, or 5 year, range of like a power purchase agreement, for example, then the likelihood, of course, the extreme cases, play most critical role. I'm thinking, sometimes we have passed, very tools. I think how long, we can simulate, probably with lower resolution in some configuration, we can do that. Anyway, thank you.
Maybe can I add to that very briefly? Yeah, so I think NCAR is probably, the CGD division, Climate and Global Dynamics division at NCAR is probably, the most advanced, although there are still things that are missing, I guess, in the integration of MPAS into the community atmosphere model. For example, one is you can't really lift the model lid or the model top too high because things get unstable once you do go into the stratosphere. There's no quasi-biennial oscillation, so there are things missing from a scientific viewpoint. Maybe that's not your interest, but the coupling is, it's there, yes, and probably stable, but I don't think it's really explored at the level of scientific rigor that we want. So I think that's actually a growing field for not just maybe NCAR, but also university community.
Comment on that? I'm looking for Zhe Zhang and Chen He, but they both are not here. Actually, within the NCAR S2S effort, we have actually run MPAS standalone, use prescribed sea surface temperature and some sea ice kind of information, run it out 60 years or 40 years, I think 20 years first. And then actually that's like what Bill said, very stable. Initialized with error 5, so just let it go, and very reasonable statistics in terms of the tropical kind of the dynamic features. So I think some works like that actually happen. And within our water system program, we also want to see the regional climate performance of MPAS. So we actually have MCube scientist Julia Kukulis running that parallel simulation of MPAS over CONUS compared to the existing long-term CONUS WRF data, try to give the community a little bit baseline on how MPAS actually compare with WRF in terms of longer time period of simulation. So yeah, actually works are there, but not at the point that give you all the information, but I think, yeah, it's actually ongoing.
Thanks, Llewellyn. All right, we're gonna go to our next question and go to the second part of a tagline for our, Gretchen, thank you. Yeah, Gretchen, go ahead.
Hey everyone, I'm Gretchen, the director of the Mesoscale Microscale Mineralogy Lab. I'm sorry, I actually live in Boulder and can't be there today. But I just wanted to follow up on, I really have had a lot of successes, but I think to continue to have successes, there have been many great examples given. I really want to lean into a lot of the comments that were made by the panel earlier of really how critical it's going to be to really collaborate in that this partnership that we have, and other partnerships have been described, but the work between NCAR and NOAA has been so fruitful, and we want to see that continue. But it was interesting in the last session, all the points brought up about being more agile, same issues that we're facing at NCAR right now. How can we provide better documentation? How do we make sure that we can use the latest tools like GitHub and continuous integration to improve the speed of pull requests? And how can we be more interoperable? All of these things. So I want to really just say, let's continue doing what we're doing, but continue to really emphasize and prioritize the conversations between NCAR and NOAA and our university partners to, when we're trying stuff out, share that information, continue to move towards solutions that are more consistent across our organizations and across within our organizations and then across our organizations, and that can be shared then with our research partners as well. We really just need to try stuff out and see what happens, right? I really we continue to do stuff, learn, adjust, learn. I do think we sometimes fall into a trap. I know we do this at NCAR of trying to build something perfect, some framework, and then we don't ever get to the trying it out and actually sharing information. So I really hope that we can all commit to that effort to try stuff out, learn, adjust, try some new stuff out, and do that as a team. So I just thanks to everybody for all that's happened already, and let's keep it up. Thanks.
Thanks, Gretchen, and thank you for being able to join. All right, we'll move on to question 2, and this leans into the second part of our title, more about community engagement. So for the panelists, what does successful community support for MPAS development look like to you? What are the gaps or needs to further accelerate that progress? Go ahead, Bill.
I'm not quite sure community support for MPAS development, quite what that means, but in essence, M-Cubed is in a position to support the community release. But as you've seen, we're going to also have the UFS with the MPAS dynamical core in it. And how we're collectively going to support that and its capabilities are unclear. And as we've seen with the UFS currently, having support for the dynamical core is an important thing in terms of moving it forward and problems people encounter, because you'll absolutely encounter problems. And anytime you bring it to a new application which hasn't been really checked out and run a lot, you're going to see things that are going to need attention. I think going forward, we're going to have to work out with our NOAA colleagues what that support's going to look like, and who's responsible for what, and what the expectations are on both sides. And that hasn't happened yet. I think we talked about that being important last year at Jackson State, maybe the year before in other venues. We have to get to that at some point soon, because it's clear that things are moving.
Yeah, quick comment. Yeah, a gap is definitely, and I think we brought it up, more education on numerics and dynamical cores for the community members to not just develop in the community the application specialists, but also the developing the new crowd that comes in the next generation of scientists. So yeah, that's definitely a gap, which maybe that's going beyond this panel discussion, because it does even need resources from agencies and also acknowledgement that this is still worth investing in. Yeah, that's maybe my 2 cents on this.
Sure. I think success, we're going to have success once we have a model that can be used for both research and operations, so that is flexible and has the usability, but that's also powerful and efficient for operations. So to me, I think that's the ultimate measure of success, is if we have a large community and also even in operations. I think in terms of gaps and needs, we do need to flesh out what Bill just talked about. I mean, we have EPIC as the main entity providing the code management and first line of support for the UFS. I see that's probably the model that we would be following, with EPIC doing general support for the capability, and then individual groups supporting their specific subcomponents, much like our group supports CCPP, possibly NCAR can support the DICOR, but of course, these things take time, energy, money, and we cannot take them for granted, so we do need to flesh them out.
So building off of what Lisa just said, so in the area of gaps and needs, one area that I've been noticing is just some clarity of where the community should be working, whether it should be the MPAS Dev repository, if it's the UFS community, what are the pros and cons of working with different forks. And so I think just a little bit of clarity for the community of what they're working with, what that gets them, and where they would go for support, I think that could help a lot.
If I could just add to that, it's going to get even more complex because it's pretty clear that if, at least, there's still going to be multiple branches of MPAS, some sitting in branches sitting in ultimately NOAA repositories, and some sitting in the NCAR repository for that. And people are going to see all these. Everything's out in the open now. Does that mean that we've got 5 minutes, or does that mean? Okay. So the world's going to get much more complex in terms of what version of MPAS did you run. It's sort of like what version of WRF did you run, but WRF has hundreds of physics options. Now it's going to be not only the options, but what repository did you pull it from, and what are the differences in that particular repository or fork of MPAS that you're dealing with. So the documentation problem gets a lot harder, for sure. And so there's a lot we need to think carefully about moving forward.
So I'll just add quickly, I think what's a successful community support is going to start with the fact of ease of use, ease of installation, ease of getting up and running. This is a mantra, if anybody heard what I was talking about the last session. That being said, I agree with Bill. Everything being out in the open is actually an advantage and a disadvantage. And I don't think that any organization, maybe in the private sector it has really, I think, figured out how to deal with this in an effective way, especially one as resource limited as we are in our collective agencies right now. So I think having a clear authoritative, if you want to come to the table fresh and new, I think that's, you can mess around with the branches, but you better, there's a base number, and that's the one that's, the main trunk. And so, but again, making things easy to get up and running, I think will get people involved in what I would call traditional NWP, and not ward them off to go off and say, well, you know what, I'm just going to do data mining and data learning, which is a very valid thing to do and probably will get them a better job later on. But I mean, we want to make it attractive for people to be able to sit down and do research if they're interested in what we're doing, and show them, have the opportunity for them to see both sides.
All right, we're coming down to our final minutes. Any other questions from the audience here in the room or online? I see one in the back, Maui. Take us home.
Yeah, I have a question to all the panelists. I think, as Lija pointed out, if MPAS has come into UFS and EPIC needs to provide the support, I kind of feel like this session is designed to inform the EPIC program. But I actually have a question to Bill and Christian, because I have heard a lot of conversations about the need for DA expertise. And some of the panelists said, okay, we need people to teach us how to use, how to couple it to other components, how to run MPAS. And then you two seem to be on the developer side. So do you have a need for future workforce development? And you seem to be very quiet about that fact.
Oh, I can see Gretchen on the screen there, so I have to be careful what I say. But yes, we have a need, and we've had a hard time finding expertise, for example, in numerical analysis and dynamical cores. And you can go down the line in terms of that expertise. As Lou pointed out, we're not training people in model development anymore. The funding to do that from the funding agencies has just dropped off a cliff. DOE, NSF, they don't do that anymore. And Christiane can tell you even more about that. So this is a problem. This is a problem. And as Lou mentioned, if you're looking for people to do model development, you look in Europe, you look in Asia.
Unfortunately, that's true. So I also will probably face a cliff that I no longer can attract funding for dynamical core education in my research group, teaching kind of the next generation the tricks. Yeah, if that mindset doesn't change in the US, we will actually go to Europe and Asia for talent.
Thank you. Does anyone else on the panel want to have a brief comment to that? Okay. All right, I think we'll wrap that up early unless there's any last comment from the audience. Excellent. Let's thank our panelists for their great information.
All right, so for our next speaker, we have Shuxia Zhang presenting the generation of grid mesh with multi-refinements for MPAS and specifically applying that to severe weather. So, yeah, welcome. Oh, there you are.
Yeah, thank you. Yes. Yeah, thank you. And it's a great opportunity for me to present the work I think I did at the DTN a few years ago when I started using MPAS, and but I realized now it can have some implication for WRF FS or for other application to achieve basically accurate forecast with enhancement of leading time. Oh, this is the machine. Oh, this one, okay. Basically, I think now everybody have discussed a lot about the rise of MPAS in the success about real efficient allocated computing resources through variable resolution and also being established as a versatile tool for both operational meteorology use and also long-term climate research. And so yeah, my present here just focus on a small piece, but it's very fundamental, important to MPAS. Same as any other numerical model is optimal grid mesh. And so basically, of course, for severe weather forecast, and we need, if I have a tell community the hour or 3 hours earlier, then we can avoid a lot of damage, rescue life. And so when I start using MPAS, I think in 2020, around the 2021 time period, so I try to use the MPAS mesh, but I had difficulty to generate some kind of additional refinement. So then I look at other tools like Jigsaw, and then which I think it worked pretty good. Then that's the reason I'm coming here to share this piece. So of course, the objective will try to help community to better harness the benefit of MPAS package. Maybe I'll go this one first. And the grid mesh provided by the MPAS team with the uniform or refinement in simple circle eclipse. And so at the DTN, so I developed the adapter tool, Jigsaw, and we developed multiple refinements. But anyway, so basically I want to thank the code developer, Darren Inglewater, for some hints regarding what I should do. And basically the piece of the key point is just the Jigsaw package has, you can specify X grade, Y grade at each grid point, then you define your resolution. And so, yeah, based on, okay, now back to, I'm sorry. What the, yeah, sorry. Oh. Oh. Okay, now, the jigsaw basically just gave a brief in the, talk about jigsaw geo. How many of you have been used this one already? No? Oh, that's a surprise to me. I saw lots of people may have used this one already, but anyway, so jigsaw is, of course, code developed by Darren Inglewater, and it has the math library is written in C++, I think, and the latest version is 1.0. It has still support and enable OpenMP. So it has both Conda installation, which you can get everything, but I recommend to do the fresh installation using compiler to better use your computing environment, and also better use the OMP support. And the Jigsaw Python is also available through GitHub, and it has the physical interface for using the Jigsaw library, and where allow we can do refine the grid mass with any arbitrary shape, which just as I showed at the previous slide I did that. And the generated mass is many triangular cell. The output format is VTK or general mass. We need to reformat it for being used with the MPass. I think here one thing I just want to emphasize, of course, the gray mass generation is not an easy task, even though people take it granted, but extremely difficult. Even I really appreciate the MPass team brought so many variety of grid mass predefined. It has a lot of work, development behind the skin, which we probably, if we do not work on them, you would just think, oh, that should be easy. We want to get some more complicated, but it's not that straightforward. But that is one thing. And of course, for a grid mass to be useful, we have to have satisfy lots of mathematical requirement, or we call the quality of grid mass. In the Jigsaw package, it provides different measures. I will talk the detail each of them later in the demo, in the demonstration case. By the way, the author, Inglewater, has a big paper, a very good paper, gave a description how the metrics were defined and what optimal value when you need to evaluate whether the grid mass is a high quality. No. Well, it does not work. Okay, how can somebody can help me? Oh. Oh. All right. Okay. Now here is demonstration case I just generated for the purpose of this presentation. Demonstrate the use of Jigsaw to generate a quite complicated grid mass. basically, in this case, yeah, for here is it is a global model. Actually, the same approach we can, okay, good, thank you. The same approach, we can use it for regional model. And we focus on the area with high resolution with the desired resolution. For here is the red color here indicate the great distance is 60 kilometer for flight area and 3 kilometer for deepest slope. And the key, the top right, the key, I call the key recipe is we upload a topography mesh file. And so we calculate the gradient. I think I just arbitrary function basically here. You can define any function based on the local x and y z define the shape. And so then this part is the key recipe, and the case 4 here is the exam cases include the Jigsaw geo package. Of course, using Jigsaw is not just a direct, easy plug-in tool. It needs some kind of it has some kind of learning curve. But anyway, so the lower part here, I just use the option to generate the matrix that characterizing the quality of the grid mass. Here I build here, the blue color, maybe just the high resolution with around 3 kilometer, and the red color indicate the area with low resolution. But the quality, basically, it has, 5 variables. It is, for the output of Jigsaw is many triangle shells. And of course, for ideal geometry, we want each of the triangle cell has 3 equal sides and 3 equal angle. In rare cases, probably the tool basically has been designed to achieve the perfect geometry shape. But anyway, so for those scores, there's like a trace score, a power score, and the rule of thumb of the value should be larger than 0.8. But in my case, for our application, I would highly suggest to get this score number close to above 0.9. For obtuse, it's 0 means all triangle angle for this triangular shell is smaller than 90 degrees. And topology just indicate the connectivity of cells at each of the vertex. And so for this, the grid mesh generated is almost close to ideal, mesh distribution. Okay, here basically this is another case. Just allow us to visualize when we generate of the grid mesh. You can zoom in to test, to visualize the quality of the connection of cells at each of the vertex. So, okay. All right, so with the Jigsaw, we generate the grid mesh, which is triangular shape. And for MPass, we need the shape called the white noise mesh. So we need to do the conversion. When I prepare this slide, I thought, yeah, most of you may know this procedure already, so then I just put something, but now I realize it may be a little bit too comprehensive. It's not that straightforward. But anyway, basically, the basic idea is that with the jigsaw, it generates the grid mesh format. We need to convert it to NetCDF format. Then through NetCDF format, and the MPass tool has the what they call mesh. It's a mesh conversion tool, and we can convert the triangular NetCDF to Voronoi mesh, which we can directly use MPass. For MPass, yeah, if we can just run low resolution grid, we can large share SMP machine, we can just use the white noise mesh for simulation. But the big advantage MPass is parallel computing. So then we need to do the decomposition of the grid mesh into multiple blocks, which the MPass tool has a particular Python file called make partition file. So then this make partition file use the tool called Metis. And Metis does the domain decomposition. I think people, how many MPass developer here? Say, Bill, you know, so you know Metis, right? So you that one, and those do the basic partition. Yeah, I'm sorry, you know, so I didn't, I just assume lots of people know the jigsaw already, so I didn't prepare lots of details. But anyway, lots of information behind just a slide, this slide. You know, each page I can talk maybe half hour easily. But anyway, so yeah, just feel free to contact me for any clarification or if you need any help for implementation this will work. I will be happy, you know, to provide some support. But anyway, so after we run the what we call Python make partition through using the Metis, it will generate graph information part B file, which is allow the parallel computing going. Basically, it for the blocks, for example, if I have a global model, I want to decompose it into 512 blocks, then it will generate the participation information there and tell which part of the grid mesh goes to which compute process. But after that, then we just use a test the newly generated grid mesh following the practice session guide in MPass tutorial. Of course, in that case, we have to replace the included grid mesh by MPass tutorial. For example, here we said X1. We call it X1. In one case, it's probably 10.42 grid NC, for example, with the one we created, we call the white noise mesh.nc. Of course, we also have to replace the graph info part .b file. Anyway, so that basically is the procedure to convert a jigsaw mesh for the mesh can be used by MPass. Yeah, so yeah, just throughout this process worked for us. And all right, okay, yeah, that is both my part of my presentation. That's basically, I try to share the key concepts and procedure to generate customized grid mass for MPAS. Of course, the objective to help community better use or better harness the benefit of MPAS. And in the context of WIFS, this approach, I create only the same approach. I did also some regional model too, but it can apply the same approach to regional model. That, of course, relative to the 3 kilometer global MPAS simulation, variable resolution should increase the lead time, and also, can more accurately capture the local geographic feature. More importantly, this work methodology would allow the WIFS system to refine the grid mass as the weather condition evolve. Looking forward, this methodology, of course, we can increase some real-time radar satellite data. We can increase the higher resolution for local area, even capture the building blocks regarding those type of applications. Even for lots of, we hear today, we have some people interested in AI or machine learning part. We still need the grid mass to do any forecast application. Yeah, but then as an acknowledgement, I want to thank Darren Engward for Jigsaw, and basically also he answered some of my questions in the beginning about in email. I want to solve this problem. How can I do that? That's really appreciate. I really appreciate that. Another way, I want to thank University of Minnesota Supercomputing Institute for some computing facilities that allow me to generate some demo case. Thank you very much for your interest, for your time. Any questions?
One just came in from online. Just wonder how long it took to generate the global 63-kilometer finishes or meshes, excuse me, with Jigsaw.
Just the demonstration cases. For that one, take I think about 2 hours. In the memory, about I think the machine memory is 500 gigabyte. Of course, in increased resolution, I think with a really high resolution, because these days the memory machine is not a big problem, but it does need some computing facilities. And with the OpenMP support, and it speed up a lot of the generation process. Of course, it still have some learning curve to figure out the configuration Jigsaw regarding how to speed up or how to get the code converged fast.
So since you started talking about performance and everything, I'll ask a follow-up question of my own. Does this framework utilize GPUs, or is it CPU only?
Right now, I didn't test on the GPU. I think since it's a C++, I'm confident it should run on GPU. And on GPU, basically, the problem with GPU is the memory. And for small size, it's no problem. But currently, GPU, I think the largest one I use about 80 gig. And so probably it won't be enough for generate the grid mass efficiently. Yeah, I did talk to the code developer, Darren, about the distribute memory version. So basically, so probably it's not an easy task.
Yeah.
Yeah, if there are no other questions from the room, if we could get a round of applause then. All right, so we are just about ready to adjourn, but first, a double raffle. So if Allison could please come up here with the bucket of raffle tickets. Our first ticket is 503. They all start with 503. 315. Does anyone have a 315? Check your pockets, maybe your backpack. I don't know where you put your raffle tickets. All right. Well, unfortunately, they went to a really cool laboratory and missed out on mugs, so